Hello, hello, hello. Good morning, good morning, good morning. Welcome aboard. Do let me know if you can see me. Do let me know if you can hear me loud and clear. This is Shreyas here, your physics master teacher. How is everyone? Good morning, Harshita, Ujwal, Smarty, Kavya. Hello, Khushi. Hello, Rishabh. Hello, Zaya. Hello, Sanyogita. Hello, Dhruv. Karuna, Aditya, Rishabh. Welcome, Sakshriti. Hello, Champion, Abhinaya. Hi, Shubham. I hope you guys can see me and hear me loud and clear. And I hope you are all with very, very high josh. Let's begin the marathon session. And this is for the Term 1 CBSE Physics. And in today's session, we are going to see the important points of NCERT. So make sure your NCERT is out. And yes, the assertion reason cases as well. So let me just quickly brief you about what and all we are going to do in today's session. But before that, a quick introduction about me. Hi Sakshi, hello Umina, hello Navina, hello Annie, me, my god, what a name. Hello Nandita, welcome aboard. Hi Roman, hi Art Bubble, hi Kavya. So, very quick introduction, I am Shreyas. Some of you might know me. I am the physics master teacher. Some of you also call me Capto Shreyas. And I have been training and teaching for almost more than a decade. And under my guidance and my mentorship, many students have not just cracked board examinations, but also the JEE, KVPY and all such competitive examinations. I am very proud to tell this to you that many of my students have got top 2-digit All India ranks in JEE Mains as well as JEE Advanced. So here I am to spread the joy of learning and make sure that you enjoy physics like never before. So if you want to know more about me, you can definitely follow me on my Instagram handle. Now, this is the flow of today's class and you should know it. Well, just one second guys, just one second. I'm just getting to know that there is no voice on biatonic. All right. Okay, so I think there was some voice problem, but yeah, I hope now it's fine. Okay, so don't worry, on biatonic, those of you who are watching, I think there might be some technical issue. Don't worry, it's getting rectified. I just got a call. And meanwhile, on Enthuse, obviously this is going live right now. Okay, so what are we going to do today? We are going to see the important points of NCERT. I'm going to make you underline some important stuff, the definitions and important paragraphs. Number 2, we are going to revise it. Also, we are going to revise it via case studies. That is, you will be given a passage. You have to take a screenshot of it. Okay, take the screenshot and then I'll ask you questions. Okay, so there are a lot of passage and case study based questions as well as assertions and reason based questions. So lots of interesting stuff. I hope you have already smashed the like button. And if you have not done it yet, please do that right now because that's the charge for today's session. Just a small like and yes, do not forget to hit the subscribe button so that you do not miss my classes tomorrow. So let's begin our today's class. Everybody's josh is high. The josh is high. Everyone done? Very good, Rishabh. Very good, Zaya Cub. Very good. Aditi says now it's fine. Well, Raj, now fine. Very good, Uncharted. Good morning. Hi, Janaya. Let's get going. So let's start with the first chapter. So those of you who are joined in late, okay, today is NCERT underline plus case studies plus assertion reason based question. It's a marathon session for physics term 1 examination with me, your Capto Shreyas. Okay, it's going to be a big session. So the first chapter in front of us is electric fields and obviously charges. So let's open up the PDF and let's start seeing all the important points out there. So here I have the PDF. I hope you have the hard copy or at least the soft copy of the NCERT in front of you. Excellent. Let's get going. Okay, so this session is going to be at least 2 to 3 hours. Okay, Roman? Okay, so now in the first chapter, let me tell you what and all are important points out here. Okay, so let's go over here. The first part is, okay, just the introduction. You can skip it. That's not so great. Now all these things over here, okay, it's just about the history of electric charge, as in when it was discovered and what happens when you rub something and how the charges get transferred. Like for example, you rub a glass rod with, you know, some cloth or plastic rod with any other material, how the charges get transferred. So this is not so great, but what you should know is over here, okay, the property which differentiates two charges, the property which differentiates two kind of charges, that is the polarity of the charges, okay, and that happens only because of repulsion. Understand, you can understand that there are two kinds of charges because of repulsion and attraction. Understand, so without that you would never be able to understand that yes, there are two kinds of charges. Okay, now going little bit below over here, this is fine. Okay, let's just go down over here. Now this is some interesting thing which you already know, but an important line. A simple apparatus to detect the charge on a body is the gold leaf electroscope. You should know about it. Okay, when you charge any body and you touch it to the gold leaf electroscope, then the charge gets transferred to that leaf, and those two leaves will repel each other because they acquire like charges. That's one thing which is right over here. Okay, that's something which you should know. Great. Now let us go below, but remember one thing, this part is not as such there in the syllabus, so that's why I've highlighted it in red. So you can directly, okay, you can directly skip this much part. Okay, I will be zooming the screen. Okay, it's fine. Okay, I've just zoomed the screen, I just saw that. Perfect. Okay, 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 cool. So this part you can directly skip, go ahead. I have marked it red, which is this section 1.3. okay, but remember this can come in case studies. Let me tell you that in case studies it can come indirectly, any even out of portion case study can come. So from that point of view you can read it, but everybody knows what's a conductor and what's an insulator, so that's fine. So going below little bit, just one second, oops. Okay, just one second. Okay, yep, my god, why is this acting crazy? Okay, now I think it works fine. Okay, cool. Going down. Now, charging by induction. If you know these diagrams, you can skip this complete paragraph. Just look at these diagrams. You will understand almost everything about it. See, you have two bodies, okay, A and B, okay. Over here, if you look at this diagrams, you will understand that the charges can get transferred from one body to the other, via two different ways. One is called, you know, induction, the second one is called conduction. Now what is the difference between conduction and induction? Those of you who do not know, quickly see in conduction. In case of conduction, let me just use my regular pen out here. I think my regular pen is only better. Okay, so the conduction, in case of conduction, the charges actually get transferred. But in induction, there is no transfer of charges. If you just have a body, the charges move internally. They do not get transferred from one body to the other. One side gets negatively charged, the other side gets positively charged. So understand the difference between induction versus conduction. So that's what this paragraph deals with completely. Okay, so you can skip this paragraph, but remember what is induction, what is conduction, that's all. That's more than sufficient for this particular part. Going little bit below, okay, you can see in this process metal spheres will be equal and oppositely charged. This is charging by induction, and you can see that here they have mentioned this definition of induction, okay, right over here. Okay, this process. Going little bit below, yes, it is basically redistribution of charges is nothing but induction. That's it. Perfect. Now I want you guys to read this paragraph properly. This is very good example of, you know, conduction and induction processes, and also how earthing works. This is a very good example, so do not skip this example. So that's why I have highlighted this. Okay, so please go through this example, that's very important. Now, simple properties of charges. There are few basic properties which you should know. There can be direct assertion based questions on it or even MCQs. First is addition of charges. The whole idea over here is just, you know, if you have n charges, then you can just add the charges. So that's it. So all you have to do is make sure that you make use of the signs, and also, you know, you just have to add all the charges as if it's a scalar quantity. There is no direction, it's a scalar. There is no direction involved here. It's a scalar quantity. That's what it says over here. Great. Then the next important point that you should know over here is total charge is conserved, and you can also remember this particular statement over here. Within an isolated system consisting of many bodies, and if there are interaction between the bodies, the charges may get redistributed, but it is found that the total charge of an isolated system will remain conserved. This has been established only experimentally. There is no theoretical proof for that. Yep, there is no theoretical proof for that. So this is very important. Okay, so this is another important line over here which you should remember. Quantization of charge 1.5.3. okay, quantization of charge. This is the important formula over here which you should remember. Q is equal to NE. It has been experimentally, there is no theoretical proof, experimentally established that all free charges are integral multiples of the basic unit of charge denoted by E. So the most important line over here. So the NE charge on the body is Q times of NE. So this is another important thing that you should know. Okay, and fair enough, proton carries a positive charge, electron carries negative charge. Everybody knows this. Okay, this is fine, but here the fact that electrical charge, this line right over here, okay, the fact that electrical charge is always integral multiple of E, this is called as the quantization principle or quantization of charge. Very important. Okay, well, going ahead now, this important experiment which is done by Milliken in 1910. In fact, we are going to do a case study based on Milliken. You should know the name. Milliken oil drop experiment was the experiment which discovered the quantization of charge. Okay, so that's why I have underlined that particular name. And obviously you should know the value of E, 1.6 into 10 to the power minus 19. That's a standard value. Okay, moving ahead. Okay, just moving ahead. Okay, going down. This is all fine. That's okay. You can just ignore this. Okay, so these are some examples you can definitely go through it. Now going to Coulomb's law. So directly in Coulomb's law, obviously the formula F is equal to K Q1 Q2 by R square. Now how did he arrive at this law? That is different, but that's not so important. Ignore that part. Go below. This is the important formula. Now go down, keep going down over here, right over here. Okay, you will have these important values. You should remember these important values. Epsilon naught's value 8.85, which is also called as the permittivity of free space. Permittivity of free space. Everybody understanding this? Yeah, we are going to cover all the chapters. Yep, we are going to cover all the chapters here. We are going to cover everything. Okay, and the value of 1 by 4 pi epsilon naught, the constant which is 1 by 4 pi epsilon naught, you should know the magnitude is 9 into 10 to the power 9. So this is the value of the value K. Okay, the constant K. Cool. So moving ahead below, okay, these are important things, and this and all is fine, but this is the vector equation which you can remember for the force. So this is again one important thing. This is nothing but your unit vector. This is your unit vector and this is your force vector. So the vector equation is something which you can remember. Moving down below, okay, now this particular relationship that you see over here, F12 is, okay, F12 is nothing but negative of F21. This is nothing but Newton's law of motion, third law. This is your third law, that's it, nothing else. Okay, so that's as simple as Newton's third law of motion. There is nothing great over there, but yeah, that's something which you can keep in mind. All right, moving down a little bit. Okay, let's go a little bit down. Okay, everyone, these are examples. Examples is something which you should definitely go ahead with. Okay, now forces between multiple charges. Now over here, whenever you have multiple charges and you want to find the net force, just let's go down over here. Ignore all these parts. Just focus on this. The net force is just the addition of all the forces. Basically, it says vector addition. That's all. It's nothing but vector addition of all the forces. Vector addition of all the forces. Nothing else. So the total force is the addition of all the forces adding vectorially. Okay, so you can use by parallelogram law, or you can even use triangle law or triangle law of vector addition. Either of the things will work. Okay, so they have given some questions out here. You can go through those questions obviously. Going down, electric field. So electric field's definition, yes, you need to know the definition of electric field and also the unit, which is Newton per Coulomb or volt per meter. Very, very important. Okay, and this formula is also important where you see, okay, just go down a little bit. Okay, on this page, the force is charge into field. The force is equal to the charge multiplied by the field at that particular point. Very, very important. Okay, cool, excellent. So I hope you guys are following me with this. Okay, if you want, I'll zoom it a little bit more so that you can see now even better. Okay, great, great. I think now it's better. Everybody give me a thumbs up if you guys are following me till here, and I hope you have started marking and going through all the points which is there in your NCERT. Let's get going. Okay, then next, this is the true definition of electric field. This is how electric field is actually defined. Its limit test charge, this Q tends to 0, okay, is basically your test charge. The force acting per unit test charge is basically called as the electric field. This is what the true definition of electric field is. So this is another important thing that you can keep in mind. Okay, this and all is fine. And yes, everybody knows this. For positive charge, electric field will be outside, and for the negative charge, the electric field is radially inwards. So for positive charges, it is outwards, and for negative charges, it is basically inwards. Okay, that's fine. Great. Now, okay, this and all is fine. You did not have to do it. It is very obvious. So I'm just underlining all the important points. Going down, electric field due to a system of charges. Again, this is very much similar to your previous forces addition. Just remember this. Don't go through anything else. It just says it is a vector addition. That's it. It's a vector addition. Don't have to remember any of these stupid formulas. It's just that electric field is a vector quantity. So that's why you have to add all the electric fields due to all the things. That's all. Perfect. Going down, physical significance of electric field and all that. That's okay. Nothing great over here. That's okay. You can skip this. In the last few days, what and all you should go through. So that's what we are focusing on. Otherwise, you will end up reading the entire NCERT. Okay, now electric field lines. Now this is something which you should know. How does electric field lines, what are the different properties and how to draw them? Okay, so electric field line is strong near the charge. So the density of field lines is more near the charge and the lines are closer. Very important line. When the density of field lines is more, the field also increases. When you go away, the density of field lines decreases, electric field also decreases. That's one thing which you should know. Okay, now this is also an important line. It is the relative density of lines which matters, because each person may draw different number of lines. So how do you compare that? So that happens by relative, comparison. It's not the absolute density. You cannot count the number of field lines. Number of field lines are infinite. Okay, great. Going down, all right, go down. This concept of solid angle and all that not needed. Cool. Now, these are some important properties over here. Field lines start from positive charges, end at negative charges. If there is one single charge, they may start or end at infinity. That makes sense, because if there is only one charge, where will it end? then obviously it will start or end at infinity. If there is a charge-free region, electric field lines can be taken to be continuous curves without any breaks. Very interesting point, you should know this. Two field lines can never cross each other because then you will have ambiguity and two tangents. And tangent always gives you the direction of the field. Electrostatic field lines do not form any closed loop. This follows from the conservation nature of electric field. So they start and end, they do not terminate and start at the same point, unlike magnetic fields. Something which you should know. Great. Electric flux. Moving ahead, what is electric flux? Okay, let's go down. Yep, there we go. Below. Yes, there we have it here. So electric flux definition. This is something which you should know. E vector dot area vector, or E electric field dot area vector into cosine of the angle between them. Okay. Now this is one thing, and moving down over here. Here you can see this is the total electric field flux, the total electric flux for a closed surface or any curved surface or any irregular shape. So this is just nothing but total flux. It is nothing but sum of all flux, sum of all the fluxes. That's all. That's what it is. Okay. So that's something which you can see. Now going to the important point, electrical dipole. So the definition of electric dipole. Electric dipole is nothing but a pair of equal and opposite charges separated by a distance of 2a. Okay. Now some books use this 2a, but if you don't like 2a, you can also write it as L. L, which is the separation, into the charge will also give you dipole. Okay. And by convention, the direction from negative to positive is said to be the direction of dipole. Okay, that's very important. And the center of the dipole is basically the midpoint between the two charges. So two charges, positive and negative, this is basically your dipole moment, and this is nothing but charge into 2a. Some books also use just L. So where 2a is equal to L. It's up to you how you want to remember it. Moving ahead. Okay. Now the electric field due to a dipole falls off very fast at a very large distance. Okay, that's another interesting thing which you should know about a dipole. So the electric field due to a dipole falls at a very fast rate. It is in fact going to be proportional to 1 by r cube. That's something you should remember for essentially electric dipole at a very large distance. Okay, that's one important thing. Moving ahead. Okay, this derivations and all, it's fine, but going to the generic formulas out here, you can see instead of 1 by r square, it is proportional to 1 by r cube. So you can see that in the formulas. Look at this. Where did it go? Yep. So you can see that the electric field formula is dependent on not r square but r cube. So this is something which you should remember. Now this formula you should know for, this is for axial points. This is axial points. That means this is the dipole and you are on the axis. But for equatorial points, if you go down below, you have the formula right over here. Yes, you can see that. This is for equator. Equatorial points means this is your dipole moment and this is your equator. That means perpendicular. So these are two important formulas that you should remember. Cool. Apart from that, nothing else you need to know. And here, just one second. Now here you have the definition of the dipole moment. You can see that this is definition of dipole moment. It is essentially nothing but charge multiplied by length. That's it. It's charge multiplied by length. Okay. So charge multiplied by the length of the dipole. 2a is the length of the dipole. Keep this in mind. Now, those of you who find these two formulas difficult, if you don't like to remember these formulas, then in fact it's a better way to remember the formula in this way, because when you write q into 2a as dipole moment, and same thing over here, q into 2a as dipole moment, the formula condenses itself and it becomes very small. So this is a better way of remembering the formula. So this is more preferred way. Okay, so this is better than the previous one. Is that okay, my warriors? All right, moving down little bit. physical significance of dipoles, that's okay. Carbon dioxide molecules, methane molecules, and whatever. You have so many other molecules, they can have polarity induced. You would have already studied this polarity in chemistry. So that's fine, you can just give it a miss. Alright, going down, dipole moment is a vector quantity. Now we come over here, dipole in external field. Okay, so if you place a dipole in external field, then what is the magnitude of the torque? So this is something which you should know. Torque is P cross E. The magnitude of P cross E is also PE sine theta, because cross product means sine theta. And this torque will not act always. It will only act when there is an angle between dipole and the field. That is something which you should know. So when P is aligned with E, the torque is 0 because theta is going to be 0 degrees. Okay, fair enough. Now, okay, let's move ahead. This is one important paragraph that you should keep in mind. Very nice paragraph. You can read it. You can have questions based on this. There are some cases given, okay, when it is parallel, when it is anti-parallel, and what happens when it is uniform and non-uniform. So an important paragraph right over here, do not miss this. Okay, going down over here, continuous charge distributions. Okay, so you have the definition of charge density, areal charge density, which is coulombs per meter square, something which you should know. Lambda, which is coulomb per meter. So sigma is used for charge per unit area, lambda is used for charge per unit meter. Okay, then what else do you have? Density, charge density. So charge per unit volume, that is coulomb per meter cube. Excelente. Moving down directly now, ignore all these things, that's not so important. What is important over here is the Gauss's law. So the statement of Gauss's law, the total flux on a closed surface, which is summation of E dot ds, is Q by epsilon naught. So that's something which you should remember. Now instead of remembering this, I'll tell you what you can remember. Okay, let's go down a little bit, a much better way of remembering this same formula. Okay, 1 second, let's go down, and here we have it. Yes, so the total flux, the total electrical flux through a closed surface is going to be Q by epsilon naught. Q is only the charge which is enclosed. Very, very important. So if you have a closed surface, whatever charges are enclosed, that's all that matters. The outside charges do not matter for calculating the total electric flux. This is the statement of Gauss law. Very, very important. Please don't forget this. This is very, very crucial. Okay, moving down over here. Okay, now over here, let me also tell you the sign convention. Yes, you will see the sign convention over here. So when it is positive, then it is out. Okay, when it is positive, then it is out. When it is negative, then it is in. That's what the whole gist of this paragraph is. You can skip reading it. That's the whole gist. Keep this in mind, you will remember everything. Now if you go down a little bit further, okay, let's go over here. Yeah, these are some important applications of Gauss law. It is applicable for any closed surface, no matter what is the shape. The term Q on the right hand side is the sum of all charges enclosed by the surface. The charges may be located anywhere inside the surface. The position, the location does not matter. Okay, so when the surface is so chosen that the surface charges are somewhere inside and some are outside, the field whose flux appears on the left hand side of the equation is due to all the charges both inside and outside. So in that formula which you have, cyclic integral E vector dot ds vector is equal to Q in divided by epsilon naught. This electric field is because of inside as well as outside, both in and out. Keep this in mind. Okay, a lot of people forget this. Okay, that's it. Now the surface that you choose for applying Gauss law is called as the Gaussian surface. You can choose any Gaussian surface, as simple as that. Usually you choose a Gaussian surface such that it makes your calculations easy. Some kind of symmetry will be there. You will either use perpendicularity, either something is perpendicular or something is parallel. So one of these conditions you will make sure that the surface will satisfy, which will make your calculations much easy. That's something which you should know. Fair enough. Now going down below over here, okay, these are just applications. Now yes, the formulas for line charge. Let's talk about this. The formulas. Electric field due to a line charge is lambda by 2 pi epsilon naught r. So electric field due to a line charge. Lambda is the linear charge density. The radial field outwards will be given by this particular formula. Next formula which you should know, the field due to uniformly charged sheet. Okay, there we have it. It is sigma by 2 epsilon naught. Okay, very important. That's it. Now this part is not there, shell is not there, so that's why I marked it in red. So you can skip it. Just ignore. Just ignore this. That's it. That's the end part, and this is a summary. Always make sure that you read the summary of any chapter. I'm not going to sit and mark points over here. Summary of every chapter should be read. Are you now ready for solving some questions on electrostatics? Electrostatics, fields and charges? Shall we go ahead with some questions? Because after this, we are going to start with lecture number 2, or rather chapter number 2 in the same class. Okay, so we're going to go with chapter 2, which is electrostatic potential and all of this. Yeah, was it useful me marking? I think you are going to save a lot of time by attending today's class. What say, guys? Yep. Let's go ahead with some questions. All right, perfecto. Let's start with some questions. Okay, let me just refresh this. Okay, let's start with this. Okay, very good Priya, very good Kulsoon, very good Tanushri, very good Nityan, Nishita, Roman, Venala, very good Arpita, very good Akash. Perfecto. Let's start with the questions. Assertion, reason questions, and then case study. Okay, chalo. Assertion says if there is a conducting medium placed between two charges, then the force between them becomes 0. The reason says reduction in a force due to introduced material is inversely proportional to its dielectric constant. Come on my bacha log, come on my warriors. Is it important to solve NCERT exemplar? Yes Nishita, it is very important. Can we get the questions in Vedantu platform for free? No, it is not for free, it is for 899 rupees. Those of you who want to attend even today's marathon sessions going on Vedantu, it is available for physics, chemistry as well as biology for 899 rupees as a whole package. Okay, some of you have started answering, some of you are saying A, some of you are saying D, one of you said B. Well, let's figure this out. Okay, looks like many of you are correct and many of you are wrong also. I think both are correct. I'll tell you what exactly is the reason for this particular question. If there is a medium which is placed, then if it is conducting, this is very important word, it is conducting. Now what happens the moment you have some charges placed over here? If you place a conductor, then the medium will leak that charge. The conductor that charge will get leaked out everywhere. So the charges will flow, it will flow out, and finally you will have no charge here. If there is no charge, there will be no force. If there is no charge over here, there will be no force. As simple as that. In fact, a conducting medium will make sure that the electric field is 0. And the way you calculate electric field is 1 upon 4 pi epsilon naught into dielectric constant into the charge divided by r square. Now you can clearly see if you use a conductor, the value of K is very high. So for a conductor, K is very high, so the field becomes tending to 0 because K tends to infinity, and because the field becomes 0, the force becomes 0. That's it. Hence option A. Understood my warriors? Okay. So field becomes negligible or 0, basically it tends to 0 because K tends to infinity for a conductor. Keep this in mind. Alright, so it's the correct reason. Moving on to the next question. Very good. Okay, now some of you are asking, sir, will I share the PDF? What do you say, guys? Do you want my NCERT PDF which I have marked? Okay, now I know then you will stop marking it in your books. Then that will be a problem. I don't want that to happen. If you want me to, I can do that. Yep, I can share that PDF which I am marking, but it will take some time. So I would say you do not become lazy and complacent ki acha sir is going to do it, so let me not mark it. Don't do that. Okay, you are going to still mark it, just that when you downloaded it, you will be double sure, that's all. Is that okay? That is fine, I guess. Aditi, Priya, Niharika, Smarty, Zozo, Khushi, everybody saying that they want it. Okay. PDF of the questions, so anyways you will get. PDF of the questions you are anyways going to get. But the problem is you have to solve it live. That's very important. PDF you can get it from so many different places. But that's not the point. How about this? 3 charges are situated. Many of you are saying option A. Okay. Let's see. Okay, looks like all of you are correct. Very good, my warriors. Looks like you guys are going to get very good marks. So the charges are situated on the circle of radius r. They form an equilateral triangle. So imagine 3 charges being situated on the corners of an equilateral triangle, and also this becomes a circle. It is very, very symmetric. Now what happens? The force on any one of them, like for example this one will be here, on this one will be here, on this one will be here. Okay, then the question is, oh, not the force on any one charge, the question is the force or the field at the center. Okay, so they are asking at the center, not on any one charge. So at the center, due to this charge it will be here, due to this charge it will be here, due to this charge it will be here. In fact, if you move these vectors, you will see that they will form a nice, equilateral triangle. You will see they will form a nice equilateral triangle, one like this one, and that one. Yep. So it's a basically triangle law of vector addition, and it completes, it's a complete, or sorry, not triangle law, my bad, your polygon law of vector addition, and you can see it completes that polygon. So there is no residual vector, so hence the net force or net field must be 0. So hence reason is also correct, and also assertion is also correct. Everybody fine till here? Very good, very good. Moving on to the next one. There is a point charge. It is lying at the center of a cube of each side, of each side A or something. It should have been mentioned. Each side, let's say A. The electric flux emanating, that means which comes out. The electric field which emanates, that means which comes out from each surface of the cube is 1/6 of the flux. According to Gauss's theorem, the total flux through a closed surface is 1 by epsilon naught. This is epsilon naught times the magnitude of the charge. What do you think? A, B, C, D. Look at this. Thank you, Darsana, for reminding me to have water. Some of you are saying A, Afa saying B, Rishabh also saying B. I think many of you are wrong. Huh? Be careful. Think carefully. What should be the correct answer? I think many of you are wrong. Yeah, the answer is B. It is not A. Both are correct, but it is not the correct reason. See, try and understand what is happening. You have a cube. Okay, you have a cube. There is a charge at the center. Yes, the flux that will come out from every face. Yeah, the flux from any face. This flux is 1/6 of Q by epsilon naught. This is correct because there are 6 surfaces. How many surfaces are there? There are 6 surfaces. So the total flux was 1 by epsilon naught, Q by epsilon naught. So 1/6 of that. But the reason says that the reason for 1/6 is that the total flux is 1 by epsilon naught times the magnitude of the charge. That too I know, but why is it 1/6? The reason why it is 1/6 is because there are 6 surfaces. Understand the difference? So, what the second reason statement is mentioning, reason is saying the flux, the total flux is Q by epsilon naught. That is why 1/6 of the flux is coming through any one surface. How is that the reason? This reason is correct, undoubtedly. Even the assertion is correct. The reason should have been there are 6 surfaces and there is symmetry. So out of the total flux, 1/6 of the flux passes through one of the surface. Then that would be the correct explanation. Is that understood, my warriors? Okay. So that's why B was correct. Moving to the next question. Very good, Niharika. Very good, Ashwan. Ashwan, no, it's not C. Okay, Muthu. Very good, Aditi. Let's move on. Yes, definitely PBSN. You will definitely get full marks, I'm pretty sure. Just stay with me till the end. For a non-uniformly charged thin circular ring where the net charge is 0, the field at any point on the axis is 0. For a non-uniformly charged ring which is circular where the net charge is 0, the potential at every point is also 0. What do you think? Figure this out. There is a ring which is non-uniformly charged. I'll help you with a diagram. Okay. So this is basically a ring. It is non-uniformly charged. Let's say it is positive here and let's say it is negative here. It's all non-uniform. And this is basically the axis of the ring and you are considering some point on the axis. This is my point P. So what do you suggest? Is the field 0? Is the potential 0? Are they correct reasons of each other? Many of you are saying C. Many of you are saying C. Interestingo. Now potential cannot be 0. Okay. Now be careful. Many of you made a mistake. See, this is why you should attend my class. Very important word in this entire statement is the net charge is 0. Net charge is 0. What does it mean? See, when you calculate the potential at point P, it will be the sum of the potential due to each point charge on the ring. Point charge on the ring. Now think about it. The potential due to any point charge, if you calculate this distance, okay, it will be 1 by 4 pi epsilon naught. You will have summation. You will have multiple charges divided by this distance. Let's say I'm going to call it small r. And this small r is same for all because it is nothing but the hypotenuse. For all the points, this distance is basically constant, correct? So the summation of this numerator, what do you think is the summation of this numerator going to be equal to? It is going to be one big fat 0 because it is given net charge is 0. Hence, the potential, the value of the potential will be 0 at that point. In fact, any point you go, you are equidistant from the positive charges and the negative charges. Understood? So reason is false. The reason is definitely false. What about assertion? Well, the field won't cancel out because field is a vector quantity. Be careful. Field is a vector quantity. So what happens if you are at this point? What you're going to see, the positive charges will give fields in this direction. The negative charges will give attractive field in this direction. You will see that there will be net field somewhere here. So if there is net field and this net is not 0, how is it saying 0? Do you see that? Okay. So, oops, sorry, by mistake I marked reason as 0. I'm so sorry. This reason was true because it says it is 0. I'm so sorry. The assertion will be false. The assertion will be false. Okay. So assertion is false. Reason is true, but it will not even explain it. Hence the correct answer should be D. Yep. Is that clear? Is that clear? Very good. So very, very interesting question. Very, very logical. Very, very interesting concept based on scalars and vectors. Yes. Assertion is false. Reason is true. Very good. Perfecto. Okay. Moving on to the next question. In a non-uniform electric field, when you place a dipole, it will have translation as well as rotation motion. And in a non-uniform field, a dipole experiences a force as well as a torque. What do you guys suggest? Thank you, Smriti, for those hearts. Okay. Let's see how many of you can get this. Many of you are saying A. Interesting. Sure, A. Okay. Let's figure this out then. All right. Correct. You guys are correct. And the answer is A. A non-uniform electric field, a dipole will have translation as well as rotation. In non-uniform field, a dipole will experience force as well as torque. See, what happens is if you have negative and positive charge, when it is uniform, the forces will cancel. Okay, the forces will cancel when it is uniform field. But when it is non-uniform field, this force will be different from this force. And it will produce a torque, and also the net force will not be 0. Because F1 will not be equal to F2 since it is non-uniform. So in a non-uniform field, there will be translation as well as rotation. Perfecto. Moving ahead to the next question. Now this is a passage. Okay, do you see this symbol? What is this symbol? Take a screenshot. Why? Because there are questions based on this passage on the next slides. Okay, so come on, take a screenshot of this. Quickly, I'll move away from the screen. I want you to take a screenshot of this passage because there are going to be case-based studies question or paragraph questions. So please take a screenshot. Everybody done? Taken a screenshot? Yep. So Ashwan, there will be the session will be till around 2 o'clock or I don't know, 3 o'clock. Perfecto. Priya says done. Okay, everybody's done. Okay, here's your first question coming up on your screen. Thank you, Sukman Singh, for all those hearts. Let's see if we can do this. There is an electron of mass m and the charge is also given. The question is, if it falls through a distance of h meters in a uniform field, then what is the time of fall? Let's see how many of you can do this really quick. Perfecto. Everybody is done. Oh, come on. Let's get this answer correcto. Very good, Himanshu. Very good, Harshita. Very good. Resh saying A. Nelson saying A. Janya saying A. Sashi saying A. Ritin also saying A. Shri also saying A. Okay, Ankita also saying A. Very good. Let's see whether it is correct or wrong. So if you have a charge value E, mass m, and then it is thrown in that electric field which was perpendicular, okay, the diagram was there, you can just go back and see, then the path will be somewhat curved and it falls by a distance of h. So it falls by a distance of h. So the question is, how much time does it take? I think this is like projectile motion. So solve it in y axis and just use this formula. Displacement in y is uyt plus half ay t square. Now the displacement in y axis is h. Initial velocity in the y axis, because it is having horizontal velocity, so there is no vertical component, so this is 0 plus half into acceleration. That acceleration was just mentioned, charge into field divided by m. Check that passage, it's just there in that passage. So here the charge is E, field is capital E, mass is m into t square. So basically mh, that 2 will also go on the top, by EE will be equal to t square. So t will be root of that. So I think that should give you answer A. Very good. Perfecto. Excellent. Moving ahead to the next question, you can see it is directly based on kinematic equations in y-axis. A is correct. When there is an electron which moves with constant speed or velocity along x-axis and it enters uniform field along y-axis, then the electron will move with uniform acceleration in x or y, or the trajectory will be either this or this. What do you guys say? Okay, very good. Dhia is loving this session. Enemy is also loving this session. Very good, very good, very good. Come on, my warriors, keep figuring this out. Many of you saying C, some of you are saying A. Well, think carefully. The electron is thrown with some velocity along x-axis. It enters field along y-axis. Then the electron will move. Okay, be careful. I think many of you are wrong in this. Guys, the field is along y-axis. The field is along y-axis. So if the field is along y-axis, force is along y-axis. If force is along y-axis, acceleration is along y-axis. The velocity might be along x, but acceleration is along y. So this acceleration will be along y-axis and it will also be uniform, because this acceleration will be E by m. Charge is constant, field is constant, m is constant. That's it, because it's a uniform field. So this acceleration will also be uniform. Option A is correct, C is not correct. Very good, chess and football. Moving ahead to the next question. There are two equal and opposite charges of mass m1 and m2. They are accelerated in uniform field through the same distance. What is the ratio of the acceleration if the ratio of mass is m1 by m2 is 0.5? Let's see. Okay. Pratiksha, exactly. Today what I am doing is I am giving you all the important topics. I am marking all the important lines in NCERT. Tomorrow what I am going to do? Important formulas, quick revision, and we are going to solve MCQs. Alright, bacha? Daya says, very easy peasy, lemon squeezy with me. Very good. Yes, theory edits, we are going to have formula revision class tomorrow at 11 o'clock. Those of you who have forgotten or who did not attend my strategy session yesterday on how to score full marks in physics, make sure you watch that, because today 11 o'clock, tomorrow 11 o'clock, formulas with problem solving, and day after tomorrow 11 o'clock, sure shot, high weightage, important questions which may very likely come in the examination on day after tomorrow. That's right. Okay, many of you got it correct, looks like it. Very good, option A is correct, because all you need to do is make use of the formula. Acceleration is charge into field divided by mass. It was given. So essentially A1 by A2 will be Q1 by Q2. Field is same, so it will be mass is below, so M2 by M1. Why M2 went up? Because mass is below and acceleration is on the top. It's clearly mentioned two equal charges. So basically this ratio will become 1. So M2 by M1 will be 1 by 0.5, which is nothing but 2 by 1. So hence answer is option A. Perfecto, easy. Yep. So moving ahead to the next one. So we'll learn the concepts via application of formula, Someshwar. So at this point of time, okay, let me warn this to you. Many students want, sir, I want to understand everything. Guys, we are just 2 to 3 days away from the exam. Now you should be on war footing. You should be on Yuddh mode. You should be on, final battle mode. That means you cannot sit and understand each and every line in NCERT. The time for that has gone. Now it's the time for just scoring marks. And I am going to tell you how to score marks. You don't ask me, sir, please explain this entire experiment again. Sir, explain this entire theory again. If you go into that, then please understand you are going to go and drift away from that full score. If you follow what I am telling, you will get full marks. I am telling you this. Okay. So, Ketki, that equation y is equal to x square, you will get it, if it is, you'll have to calculate it, and that constant of x square need not be 2. That depends on the charge, it depends on the mass. That constant also will vary depending on the masses and the field. So who says that the constant should be 2? That's another problem. So that's why that option was not correct. Okay, so what about this? Many of you are saying B, I can see that. Well, this is correct. A charged particle, when it is free to move in electric field, it will travel in the line of force. It makes sense, because if this is the direction of field, okay, and if you place a charge, then there is a force acting on it, and that force is charge into the field. That's what it is. So it goes along the direction of the force and the field if initial velocity is 0. Why this condition is important? Because if you take a charge and if you throw it this way, it won't go in the direction of field. It will go in a curved path. So that's why this condition is also important. Option B. Is that correct? Everyone? Very good. Next question coming up on your screen. All right. Yes, Ashish, you're going to get the PDF of all the questions. Don't worry. Okay, like I told you. All right. So let's move ahead with the next one. Okay, here we go. Yep. So what about the next one? A particle of mass m carrying charge q is kept at rest in a uniform electric field E, and then it is released. The kinetic energy gained by the particle when it moves through a distance y is how much? Come on. If it was a non-uniform field also, it doesn't really matter, Devi Krishna. The charge should be at rest. If the charge is at rest, then it will move in the direction of the field when the velocity is just 0. Once it acquires velocity, then it can drift away because of the momentum and because of the mass. Okay, I hope that makes sense. Okay, many of you are saying A option. Well, I think many of you are wrong. Read the question. Kinetic energy is nothing but the work. How did I get this? This is work, kinetic energy theorem, which you studied in 11th standard. You studied this in 11th standard. And what is work? You studied this. Force into displacement. What is the force? Force is nothing but charge multiplied by field. And this into displacement. What is the charge? The charge is Q. What is the field? It is E. What is the displacement? It moves through a distance y. That's it. Q, E, Y. It was very easy. So easy. Many of you said B. Very good, Selvendran. Very good, Uncharted. Finally, very good, Akash. Very good, Dasan. Okay, perfect. Option B is correct. Okay, ready for the next passage? Okay, take a screenshot. Do you see this symbol? You have to take a screenshot of this. Take a screenshot of this, my warriors, quickly. Okay, because there are going to be amazing questions based on this now. Okay, come on, let's see if you can do this. Just hold on, my light just went off. Let me just do a small adjustment. Okay. Okay. Huh. Okay, come on, my warriors. Let's see. Okay, done. Yeah. So there we go. I hope you have taken a screenshot of this. Moving to the questions part of it. Here we have it. Okay, chalo. There we go. If there is a drop of mass this much and it remains stationary in field of this much, then the charge of this drop is how much? So yes, Tanmay, what we are going to do is we are going to have, Tanmay and Mohammed, we are going to have even more difficult questions day after tomorrow in short 60. Okay, in fact more than 60 questions. We're going to have the tough questions as well just before the exam. Today I want you to understand the concepts, clear all your basics, everything should be known. Tomorrow formulas and the applications will also have good questions, and then day after tomorrow very good questions. Okay, Himanshu, done. Okay, many people do not know much about this. Well, if you read the paragraph carefully, it is describing the Milliken oil drop experiment where it says that a charge, this charge is basically floating or basically at rest. It is just lying in that environment. There is a weight force which is mg downwards, and there is field force which is charge into field upwards. They are balancing each other. So that's all that is there. So use that and you will get the answer. That's it. So mass of that drop is 1.08 into 10 to the power minus 13 into g. This weight should be equal to the force of electrostatics. What is the electrostatic force? Charge into the field. Field is nothing but 1.68 into 10 to the power 5. So therefore Q will be equal to, now 1.08 if you multiply it by 10, G, it will be 1.08 into 10 to the power minus 12 divided by 1.68. Now here you have into 10 to the power 5. Now if you do the math, I think you are going to get 0.64. You just try this out, most likely you will get 0.64. Okay, and into 10 to the power minus 17. Yep, just check this out if you are getting it. So just check this out, guys, if you guys are getting this much part, and you will get this as 6.4 into 10 to the power minus 18. I think there is a difference of the power. I think this should have been 10 to the power 14, guys. I think this is 10 to the power 14, my bad. This should have been 10 to the power 14. If it is 10 to the power 14, then it will come perfectly. Okay, then this will become 10 to the power 13, and then these things will work out properly. This will go 10 to the power minus 18, and this will become 10 to the power minus 19. I think this was 10 to the power minus 14, and then the answer will come out to be A. Perfect. Just check this out. Yeah. Just see if you're getting this. Yep. Perfect. Yeah. So a small correction. I'll correct this in your final PDF. So yes, that's the answer. Option A. Yeah. Very good. Excellent. A. Great. Moving ahead to the next one. Okay. 10 to the power 5 is from here. The field was 10 to the power 5. Okay, that's why. Okay, so what just happened in this question? See, this charge was at rest. The charge was at rest. Mg was down. The field's force was up. So Mg was basically QE. And this was 10 to the power minus 14. So just substitute the value of M from here. G is nothing but 10. Charge is something which I don't know. Field is from here. So the question is just find out this charge. Now you can do it. Understood? Cool. It's not about deleted portion, Rohrer, Pablo. This is about, it is a case study. In case study, you can get anything. Okay, it might come from deleted portion, it can come from previous years, it can come from actual portion. You do not know about it. Okay, perfect. So I hope that is clear. Yes, that's all. Mg is equal to QE. Read the passage, guys. I don't think you read the passage or you did not take the screenshot. Just read it. Here it is mentioned, it is suspended upwards. QE is just equal to mg. I think you missed this part. Just read this part. You can see this is the most important statement. All the problems are just based on this. QE is just equal to mg. That's all. Look at that. Okay, perfect. Moving on to the next question. How much extra electrons are there on this drop from the previous question? Now in the previous question, you just got the value of charge as 6.4 into 10 to the power minus 19 Coulomb. Now how many times of 1.6 into 10 to the power minus 19 is it? How many times of 1.6 is this? Think about it. Obviously the value of n, 16 4s are 64, so n is equal to 4. So there are 4 electrons. How many electrons are there on this drop which was given? So that's why n is equal to 4. Where did I get this from? From the previous questions. From the previous question I got this value. That's all. Perfect. So I think A option should be correct. Yes, it is. Perfect. Moving ahead. There is a negatively charged oil drop. It is prevented from falling under gravity by applying electric field. Mass is given. How many electrons are there on the drop? Again, same concept over here. You have that charge. There is a field force upwards and there is mg force downwards. And this is at rest. Again, start from the same thing. QE is equal to mg. But Q will be, the question is how many number of electrons are there. So Q will be nothing but number of charges into charge of each electron. So E will come as it is and this will be just mg. So N will be nothing but mg by EE. Now just substitute everything and you will get the answer. What is the mass? The mass is 1.6 into 10 to the power minus 3 grams. So into 10 to the power minus 3 will be just the kg. G value is 10 divided by electron charge is 1.6 into 10 to the power minus 19 into the field. How much is the field? Field is nothing but 100. Now just do the math. Come on my warriors, quickly. Come on, many of you are saying C option. Let's figure this out. 0, 0 just goes. 1.6 goes. And I think this 10 goes. This will become 10 to the power minus 18. And this 10 to the power minus 3 with this will become minus 6. So this will become 10 to the power minus 6 plus 18, which is 10 to the power 12. So 10 to the power 12 is option C. Just check this out. Just check this out. Okay. All right. Yeah. Just check this out if it is C. So earth field is 100. I'm not sure. Chess and football. It could be anything. Okay. Just check this out. Are you getting it as 10 to the power 12? Very good. Very good. No, I think for study you made a mistake. I think you forgot either this is a gram, you forgot the power, or you forgot some conversion somewhere. Just check it out. Yeah, it should be option C. Yes, it is option C. Perfecto. Very good. Let's move ahead to the next one. The important conclusion of the experiment about the charge is, now if you have forgotten the passage, just go back a little bit. Just go back and read the passage carefully. What is the important conclusion? Because he won the Nobel Prize for it. So what's the important conclusion of this passage? Come on quickly. Try to, the important conclusion of that experiment. Yep, C, very good. The charge is quantized. So he won Nobel Prize exactly for this. And he said Q is N into E. This is nothing but, N into E. This is nothing but quantization of charge. Charge is quantized. Perfecto. Excellent. Now the next question is very interesting. If in that experiment the charges on the drops are found to be 8, 12, 20 microcoulomb, then what do you think is the quanta of charge? What do you think is the smallest quanta of charge? I'll go back to the passage again. How did he get the value of E? He saw that every time he calculated the charge, there are always some integral multiple of some number. They found it is integral multiple of some number, and that number came out to be 1.6 into 10 to the power minus 19. So over here, what do you think is that number? 8, 12, 20. Just find out the greatest common factor. What is the greatest common factor, GCF, of 8, 12 and 20? I think it is 4. Right? Very good. Very good. Very good. Excellente Amar, excellente Selvendran. Very good. That's all. Excellent. 4 is the thing. 10 etc. cannot be the answer. Now remember, you are going to get the entire PDF of today's session in our Telegram channel. So if you have not yet joined it, please join it now. Shall we move to the next chapter, electrostatic potential? Yep, let's open up NCERT. Come on, quickly let's go to NCERT and let's talk about electrostatic potential and capacitance, see the important points, and then do assertion reason, and then also do case studies based on that. All right, perfecto. Okay, cool. Open up. Let's go to capacitance. Okay. Okay, let's just go down over here. Okay. Okay. Now this, yeah, this is basically the definition over here. 1 second, I'll just put it over here. Okay. Yeah. Yeah. So the work done by external forces on a moving charge. One important formula, but you don't have to remember it specifically. This was also there in your 11th standard. This is the basic definition of work, because dW is F dot ds. So total work is integration of F dot ds. That's standard. Okay. Now this is the definition of potential energy. This can be used in certain scenarios in MCQs. Okay. So very important thing. The work done, okay, by the conservative force is always negative of the change of the potential energy. Okay, so negative of the change of the potential energy is something which you should remember. Okay, now all this is fine, but over here, okay, the work done by electrostatic field in a moving charge from one point depends only on initial and final points, independent of the path taken. And this is fundamental characteristic of conservative force. Very important line over here. Going down. Okay, going down. Okay, fair enough. Okay, now here it just says that reference. It talks about reference potential energy. You can choose anything. So the difference of potential energy which is significant, and any arbitrary constant can be added to potential energy. See, what it means is, like when you have solved energy problems, you can take ground level as 0 potential energy, you can take height h as potential energy as 0, you can take bottom as 0 energy. What matters is how much is the change in the potential energy, because change in potential energy gets converted into kinetic. So you can assume anything as 0 reference. Relative potential energy is what matters. The difference of potential energy which is what matters. That's what it says. Okay. But usually what do we take as reference? Usually we take infinity as a reference. Okay. So when you take potential energy at infinity, you take it as 0. This is your general standard reference for potential energy. When you are separating charges or masses by infinite amount, you assume it to be 0, and with respect to that infinity's separation, you calculate the potential energy. That's what is usually done. Okay, great. So that's why you can see the definition right over here. The work done by external force, okay, in bringing the charge from infinity to that point, that is basically defined as the potential energy. Okay, as a standard definition. That's something which you should know. Okay, now we'll talk about potential. So potential is nothing but work done per unit charge. So here is where you have the definition. Work done by external force in bringing unit charge from, infinity to a point is called as electrostatic potential at that point. That's the definition. Okay, again, as we have done before, the potential is 0 at infinity. So at infinity, potential is basically 0. That's our reference. Moving down. Okay, electrostatic at potential, all this is fine. Okay, this is all fine. Great. Now potential due to a point charge. Okay, here we have it. This is the formula. Remember, potential due to a point charge, 1 by 4 pi epsilon naught q by r, and this is a scalar quantity. Potential energy are scalar quantities, so there is no vector equation right over here. Okay, similarly, these are the graphs. You should remember these graphs. This graph is important. Okay, So do not forget how the graph of potential changes with respect to distance. Great. Moving potential due to electrical dipole. Yes, moving to dipoles potential. Okay, so if you have two charges, this charge will create potential, this charge will create potential, this is your dipole. Okay, so at any distance r which makes an angle theta with the dipole, what is the potential? Moving down, you will get the formula. Okay, there we have it. Yes, here it is. The potential is 1 by 4 pi epsilon naught p vector dot r hat vector divided by r square. This r hat is nothing but the unit vector, or rather I would say, just one second, unit position vector. Unit position vector, very, very important. Okay, so I put it right over here. Moving down. Okay, now where is the potential 0 and where is it not 0? I'll just give a simple diagram. This is a dipole basically. So on the equator it is 0, on this side it is positive, on this side it is negative. That's all. That's the gist of the entire paragraph. You don't have to break your head over this. That's what this says. Okay, so this is the summary of whatever is written down right over here. Okay, potential due to dipole depends on the distance and all of this. This is fine, but this is an important line. The potential falls off. Okay, the potential falls off at a very fast rate. It's not 1 by r, it's 1 by r square. Because if you see the formula for potential, it has got r square below. Usually the formula for potential used to have 1 by r. Here it is 1 by r square. So it falls off much faster than your regular potential. Now due to multiple charges, what do? Just add the potential. You can see that if you have multiple charges, just add the potentials. It's a scalar addition. Scalar addition. Direction does not matter. There is a charge here, 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 here. Potential at this point, due to this, everything, you just add them up. Perfect. Moving down. Okay, let's just go down. All these are not so important. Just go down below. Okay, this is fine. Go down. Perfect. Let's just go down. Okay, yeah, this particular example is again very important. Please go through it. It will give you the idea of how to check potential difference and all these things and the field lines. Okay, the relation between potential and field lines. Now equipotential surfaces, let's just go down. So yeah, okay, here it is, very important line. For any charge configuration, equipotential surface through a point is perpendicular to the field at that point. Okay, this is very important line, remember this. So what is equipotential line? Equipotential surfaces are nothing but where potential is constant, as simple as that. You mark all the points where potential is constant, you will get equipotential surface. Okay, now okay, you can see over here as well, these are surfaces, these are V is equal to constant, and you can see this is electric field, you can see it's perpendicular everywhere. So these are equipotential surfaces and these are electric field lines, very, very important. Some more electric field lines and potential surfaces which you should know right over here. All these are very important. Okay, they can give you in questions. Okay, next, the relation between them, very, very important. This electric field, okay, or rather I would put it like this, generally electric field. Okay, sorry, just one second. Yeah, so the electric field is negative gradient of potential. Okay, potential. So what is gradient? Gradient means rate of change of some quantity with respect to distance. So dV by dl, it just means it is rate of change of potential with respect to distance. What does this negative sign signify? The negative sign signifies the direction. So electric field is the direction of is in the direction at which the potential energy decreases. So that negative sign stands for that. Okay, and the magnitude of this is the change of the magnitude of potential per unit displacement, which is also called as the potential gradient. Very, very important lines right over here. Okay, perfect. Okay, moving down, potential energy for a system of charges. So when you have multiple charges together, then what is the total potential energy? Let's go to that. Here is the first formula. this formula is for two charges. This is Q1, this is Q2, this is the separation, this is the potential energy. 1 by 4 pi epsilon naught Q1 Q2 by R. That's it. There is no R square. R12 is the distance between the two charges. Perfecto. Let's move ahead. Okay, there is nothing great here. Nothing great here. Okay. Yes, and this is all fine. Okay. This potential energy is the characteristic of the configuration of the system. As in, it does not matter how you achieved it. What matters is the final assembly, final configuration of the system. It is independent of the manner in which you assemble it. The reason for that is because it is conservative force. It is conservative field. So because it is conservative, the manner in which you assemble it does not matter at all. Perfect. Now there is one more thing which probably I think I might have missed here. But yes, I will just put it over here. The entire gist of this, paragraph is that the potential energy is the charge into the potential. This is another formula which you can remember, because potential is energy by charge. Okay, so you can also write energy is charge into potential, one and the same thing. Okay, so this is another important thing which you can remember. Moving down, they have given some examples of how to calculate potential energy. Okay, potential energy of a single charge is not there. Okay, I think that whatever I just gave you, Q is equal to V into R, potential energy is Q into V. Whatever I just gave you is just over here. So yes, that's another important thing. Moving down, this unit conversion, very, very important. What is 1 electron volt? 1 electron volt is 1.6 into 10 to the power minus 19 joules. Very, very important. 1 electron volt. A lot of people forget that conversion. Keep this in mind, it will be very useful. Going down, going down, going down. All this is fine. Energy of a dipole in some external field. Just like you have seen that there is a torque which acts on a dipole, same way there will be also energy of a dipole, and that energy of a dipole in a field is given by this formula. Very, very important. U is nothing but minus P vector dot E vector. So this is that formula. Please keep this in mind. Please keep this in mind. Okay, very, very important. This is also PE cos theta. And remember, what is the reference? The reference is mentioned here. It's mentioned clearly over here. The potential is taken to be 0 when the angle is 90 degrees. Very, very important, for 90 degrees. So when there is field here and the dipole is like this, then the potential energy reference is taken to be 0. Keep this in mind. Perfecto. Chalo, let's move down. Okay, now we have inside a conductor. These are important properties which you should know. Like inside a conductor, the field is 0. At the surface, the field is perpendicular. This is again important property. Again, the third property, the interior of a conductor can have no excess charge in static situation. That means all the charges are always on the surface. Very important properties out here. Then the fourth property, electrostatic potential is same everywhere because field is absent. When field is not there, the potential will not change. Everywhere on the conductor, it's having the same potential. Again, the field on the surface of a conductor is sigma by epsilon naught. It's not 2 epsilon naught. Be careful. It's not 2 epsilon naught. It's just epsilon naught. Okay, that's what it is. And the concept of electrostatic shielding is also mentioned over here. It says that if you have a conductor and from outside you have electric field, if you have a conductor, it will make sure that the field inside the conductor will become 0. And if you are in that cavity of such a conductor, the field will not be there. So you have indirectly been shielded from the external field. That's what it is. Okay, very, very important. Okay, so these are some basic things which you should anyways know. Now, dielectrics and polarization. So dielectric constant, I already told you, you can skip all this. This is all not important. Just remember, okay, all these things are not so important. Just go, I'll just give you the gist of this. Just remember, the force in any medium the force in any medium or field in any medium will be field in vacuum divided by K. This is called as your dielectric constant. Dielectric constant. Just keep this in mind. That's the whole thing of this entire paragraph. All right. Okay. This will be used sometimes. Maybe they might add dielectric in capacitor. So that's when you might need this just by chance. Okay. All this is okay. Now let's just go to capacitors. Very important formula. Q is equal to CV. Okay. Q is equal to CV. All right. Perfect. Let's go ahead. C is called as the capacitance, and yes, okay, and it only depends on, very important, geometrical configuration, shape, size, separation of the system. Very, very important. Okay, and one more thing. Okay, just 1 second. One more thing which it depends on. It also depends on the nature of the insulator, which is dielectric separating the medium. So if you put a dielectric, the capacitance will change. Okay, the symbol, everything is mentioned, unit is mentioned, all this is okay. Parallel plate capacitor. Okay, now over here I'll tell you what you should remember. This is what you should remember. Where did it go? The formula for a capacitance, epsilon naught A by D. Is it there somewhere? Okay, I don't know where it is, but yeah, I'll just put the value of capacitance. Capacitance for parallel plate, it's epsilon naught K into A divided by D. So this is the formula which you should remember. If you remember this, it becomes very easy. Okay, then effect of dielectric, like I was saying, when you add dielectric, I have already mentioned it right over here. Right over here, when you add dielectric, capacitance will increase. So that's it, it increases K times. So that's all that is there over here. So you will see it right over here. The capacitance increases K times. Very, very important. So the capacitance increases from its value in vacuum. Very important line right over here. Moving ahead, moving down, combination of capacitors in series and parallel. Okay, standard. This formula is for series. This is for series, and keep this in mind that the charges are same. Where is it given? Okay, charge on each, this would result in the, okay. Okay, yeah, this is what is the important line. In the series combination, the charges on the plates are same on each capacitor. This is very important. All the capacitors have the same charge. Going down, capacitors in parallel, this is the formula. Okay, you just use the reverse formula of resistors. In resistors, what happens? In resistors, what happens when they are in parallel? It is 1 by R1 plus 1 by R2. But in capacitors, it is just C1 plus C2. That's what is different. And in capacitors in parallel, all the plates are at the same potential. You can see voltage is same. Okay, so the same potential difference. In this case, same potential difference is across all the capacitors. Very important line. Okay, going down, energy stored in a capacitor. Directly remember the formula. Where is it? It's right over here. Different forms. Half Q square by C, half CV square, half QV. One and the same thing. You can remember it any way. Okay, going down. And there we go. Energy density of the field. Energy stored per unit volume in electric field is half epsilon naught E square. Important formula, do not forget it. Going down over here, yeah, that's it. Summary. Obviously you cannot skip the summary, so summaries of every chapter are important. Okay, so 2.43. okay, I think I would have marked everything by now. Okay, let's see if I have missed anything. Cool, everybody give me a thumbs up if you have got it till here. Yeah, everybody fine till here. 2.43, let me just go a little bit up. Acha, oh, right over here, yes, the capacitance formula, epsilon naught A by D. I have also added K, which also gives you basically the effect of dielectric. So this is the same thing. Yeah. Cool, yes, very good, very good. So let's go down. So till summary, whatever is there, please make sure that you do it. And if you, yes, points to pointer also are important. In case I have missed it, let me just put it right over here. Yes, points to pointer. Yep, please don't miss this as well. Very, very important. And also you have a chart of Okay, is this important? No. This is not important because you cannot sit and by heart the dimensions. So please don't sit and by heart the dimensions. But if there are values given, yes, then you have to sit and remember those values, but don't sit and by heart these dimensions. Symbols you already know, unit also you know. This is not so great. This is not so important. What is important is the summary and these points. That's all. Okay, cool. Very good. Chalo. So I think this would be very useful for you for revising. I have marked all the important things. Iske baad na you will find it very, very easy to revise. Okay, how many of you think by tonight you will be able to finish almost entire NCERT revision so that tomorrow and day after you can just focus on problems? How many of you think that? Yes, we are going to do all the chapters. Energy stored in capacitor also done. Yes. Okay, chalo. Let's do some questions based on this. Okay, after this chapter we will do current electricity and then we'll have a break. Yes, after this chapter we'll do current electricity and then we will break for maybe 10-15 minutes, not now. Let's do this. A parallel plate capacitor is connected across the battery. There is a slab of constant K introduced between the plates. The energy stored becomes K times. The reason says surface charge density remains constant. What do you guys say? Van de Graaff generator and all that is not there, Shinto. Don't waste your time over there. Please don't waste your time there. Yes. Sir, can start NCERT exercise questions? Yes, you can do that. And Anu, we are going to do even more questions tomorrow and day after tomorrow. Very good, Anishka. Very good. Chalo, let's see. Many of you are saying option A is it? B. Some of you are saying B. Interesting. Okay, let's find this out. Okay, so the correct answer is actually B. And let me tell you why. And many of you were correct. Some of you went wrong. There is a parallel plate capacitor in which is connected across the battery and you add a dielectric. So when you add some masala, when you add some dielectric constant right over here, the capacitance will become K times. The capacitance will become K times. That's a standard thing. And the moment capacitance becomes K times, because Q is equal to CV, this voltage is constant because it's a battery. This voltage is constant. Why is it constant? Because it is connected across a battery. So that means voltage is going to remain the same. So if capacitance increases K times, the charge will also increase K times. And the energy, which is half CV square, that will also become K times. Now see the facts. The capacitor has been added with some dielectric material. So because of which the energy becomes K times. Yes. The energy definitely becomes K times. The surface density of the charge. Okay, what is the surface density? Sigma will be charge by, let's say, I'll put it like this. The surface density of the charge remains constant or no. Okay, so the field is sigma by epsilon naught. The field is sigma by epsilon naught. Now, think this way. If I write sigma, sigma will be epsilon naught into E. Now, can I do something with E or else? Let me do one simple trick. Acha. I will write down sigma is charge by area. The charge increases K times. If the charge increases K times, sigma will also increase K times. And that means the surface charge density on the top of the plate remains constant. Oops, this is wrong. How will the surface charge density remain constant? Be careful. I think this answer looks wrong to me because the surface charge density, which is charge per unit area, since the charge increased K times, surface charge density will also increase K times. So assertion is correct, but reason is false. So I think option C is correct. Okay, there is a mistake out here. Did you see that? Very good, Roman. Very good, Alsari. Very good, Shri. Yep. Yes, Samisran, you will have the session PDF later on. Yep, it should be C is correct. Okay, B is not correct. Many of you marked B, and when I showed you the answer slide, everyone was like, yes, sir, B is correct. But actually, in the surface charge density, how will it remain constant? Look at this. Q is CV. V is constant. C increases K times. Charge increases K times. Numerator increases k times. Area is constant. Surface charge density also increases k times. So that is the answer. Moving to the next one. Perfecto. Yes, obviously for study, I'm sure. Okay, that is wrong. Electric field is always normal to the equipotential surfaces and along the direction of decreasing order of potential. Then negative gradient of electric potential is electric field. Come on, what do you guys say about this? Come on, come on, come on. Uncharted saying A. Figure this out. Think about this. No, Mehal, it does not remain constant. That's wrong. Okay, it will change. In the previous question, you just saw the surface charge density will change because that's the charge which is accumulated. What does dielectric do? It changes the capacitance and it can accumulate more charge. So when you add dielectric, basically you are now going to store more charge than before. So how can the charge density remain the same when you are storing more charge? Think about it logically. Okay, many of you are saying A. Well, that answer is correct, and the reason for that is electric field is negative dV by dr, and this dV by dr is nothing but potential gradient. So negative gradient of electric potential, that's what this is. And we already seen that electric field is perpendicular to the equipotential surfaces. It's always normal and it is in the direction, this negative sign signifies it's in the direction of low voltage to it's in the direction of low voltage from the high voltage. That's what it goes, from high voltage to low voltage. That is perfectly correct, option A. Moving on to the next question. Perfect. If you disconnect the battery, then the charge will remain constant. Yes, so some of you had that question, sir, what will happen if in the previous question the battery was not connected? Then the charge will remain constant, surface charge density will remain constant. So that's in the case of disconnection, not in the case of connection. Be careful. Okay, moving ahead. Work done in moving the charge between 2 points in uniform field is independent of the path followed by the charge between the 2 points. Electric forces are non-conservative. What do you guys say? Negative gradient means negative sign with the gradient. That's all. So negative gradient. Those of you are asking what is negative gradient. First of all, understand what is the meaning of gradient. Gradient means rate of change with respect to distance. So negative potential gradient. Gradient means rate of change with respect to distance of potential. Negative says that you are going towards lower potential, decreasing potential. So this negative stands for decreasing potential. That's all. Okay. What about this? Many of you are saying C. Okay. The correct answer is actually C. Yes, A is true, but R is false. Let's see whether it makes sense. The work done in moving a charge, let's say I have a charge, I move it, is independent of the path followed, and that's because it is conservative, not non-conservative. It should be conservative. So this is false, this is true. Perfect. Okay, that's a property of a conservative field. Moving on to the next one. Charge on all the capacitors in series is same. Capacitance of capacitor is directly proportional to the charge on it. What do you say about this? Looks like an interesting question. Come on, come on. Will NCERT line by line do help? Yes, Keshav, because it's a CBSE paper, bacha. Obviously, it's going to help you for the NCERT CBSE based examinations. Let's go ahead with the next question. Everybody saying A and B and C. People are confused. Charge on all the capacitors. I just made you underline this particular statement in NCERT. The charge on all the capacitors is the same. Capacitance of capacitor is directly proportional to the charge on it. This is wrong. Capacitance depends on shape, size. It depends on the material which is there inside of it. It does not depend on charge. Many students make this mistake. Q is equal to CV. Sir, charge increases, capacitance increases. Wrong. Capacitance increases, charge increases. Charge increases, capacitance does not increase, voltage increases. Capacitance just depends on these three things. Keep this in mind. Perfecto. So C, A is true, B is false. Our reason is false. Moving on to the next question. Conductors having positive charge and volume must also have same potential. Potential depends only on charge and volume of the conductor. Very interesting question. PDF Kidekuma. PDF, you will Kidekuma only. Yes, you are going to get it. Matlab you're going to get the PDF after the session, Sanjit. Okay? So PDF is going to be Kidekuma. Don't worry about it. Okay. Do you get Tattva material, Aslam? If you join the Pro, yes. If you join Crash, you get a different kind of material for the Crash. All right. Cool. Oh, is it not Kidai Kuma? Kidai Kuma. Is it Kidai Kuma? All right. Cool. So what about this? Conductors having positive equal positive charge and volume must also have same potential. No, this is not correct. Doesn't look correct. Both are false. Both are false. Both are false. Guys, it also depends on the shape. Where is the word shape? That shape is not there. If you take a square, if you take a circle, if you take a sphere, if you take a cone, do you think potential here will just depend on the charge and the volume? What about the shape? In fact, the formula, you just know this, for a ring is different from a sphere, from anything else. So it depends on the shape as well. So it says only on the charge and volume. Wrong. Charge, volume, as well as charge, volume, as well as the shape. So that's why D. Okay, time for some passage based, case study based questions. So what does this symbol tell you? You have to take a screenshot. Take a screenshot because there are some questions based on this passage on the next few slides. So if you know these formulas from this passage, you will be able to solve this. Come on, let's do this. I'm just going to move aside. Please take a screenshot of this particular passage. Just do this, and once you have done this screenshot, please put up a red heart in the chat box. Once you have done taking the screenshot, please put up a red heart in the chat box quickly. Wow, I can see all the lovely red hearts. Woohoo, nice, nice. See what and all I had to do to get red hearts from you. Life of a YouTube teacher. What and all Shreyas sir does to get red hearts. Thank you so much. Thank you so much. Okay, chalo, let's get going to the next question based on this passage. Okay, so by the way, what was this passage all about? This passage tells you just that if you have a solid conducting sphere, it is also a capacitor, and the capacitance is given by 4 pi epsilon naught r. This is the main thing of that passage. That's all. This thing over here, the capacitance of an isolated sphere. That's it. So what is the capacitance of, if you have a capacitor of capacitance 50 picofarad, then what do you think is the radius of it? That's it. Okay. Thank you so much. Oh my God, Kushal, your heart is broken. What happened? Somebody left you? Or did maths and English break your heart? Don't worry, physics will put your heart back. Okay, don't worry, we are going to mend it. Let's see how many of you can solve this question. What you need to do in this question? Think carefully. Capacitance is given, radius is asked. Which formula are you going to use? Think carefully. Yep. Uncharted saying B, Chinmay confused between B and C. So the formula that you need to use, go back to the previous slide, it is saying 4 pi epsilon naught r. This 4 pi epsilon naught, I can write it as 1 by 4 pi epsilon naught. Deliberately I have written it like this. Reason is, okay, C is 50, pico is 10 to the power minus 12, nano is 10 to the power minus 9. This quantity I know is 9 into 10 to the power 9 into R. So basically R will be equal to 50 into 9 is 450 into 10 to the power minus 12 into 10 to the power 9. So this will become 45 into this will become 10 to the power minus 3, 10 to the power minus 2 meters, which is 45 centimeters. It's not meters. I know many of you got this number but were confused whether it is centimeters or meters. Very good Selvendra, very good Brajesh, very good Arpita, Khushi, Kana, very good Suparja, very good Dhanushri. Excellent. Moving ahead. Option B is correct. How much charge should be placed on a capacitance of 25 picofarad to raise its potential to 10 to the power 5 volt? How much charge should be placed on a capacitance to take its potential to 10 to the power 5 volts. This is such an easy question. Even if you have not studied the passage, you will still get it. Arpita, very good. Fear of physics. Kushal, don't worry. Only when you love something, you can get it. If you don't have that love, then you will obviously be scared and then you will get less marks. So that's how it works. Alright, chalo. Let's see. Q is equal to CV, yaar. Come on, please do this. So 25 into 10 to the power minus 12 into 10 to the power 5. What is it going to give you? 25 into 10 to the power minus 7, which is 2.5 into 10 to the power minus 6. Correct? Which is nothing but 2.5 micro Coulomb. That's it. Yes, option D. That's all. Okay, this was an easy one. Let's go to something else. What is the dimension of capacitance? Now, yeah, don't cheat. Don't look at NCERT because I have told you, do not by heart the formulas. Let's see, you can derive quickly within 1 minute. You will have some question maybe on dimensions, and will you be able to get the dimensions of that physical quantity in that matter of time? Okay, what can you do? Q is equal to CV. Acha, wait a minute. Voltage, I can do something. Think about it. Thank you. Oh my God, somebody just spent 100 rupees super chat. Oh my God, who is that? Let me just scroll up. Oh my God. Thank you so much, Sarvana Kumar. It means a lot. You don't have to do it, but I'm really humbled. Thank you so much. Okay, so Q is equal to CV, chalo. And then what else will you do? What else will you do? Think voltage is nothing but work done per unit charge. Work done per unit charge. So if you take it properly, it will become Q square by work. And Q square, charge is nothing but current into time. So whole square. What is work? Work is force into displacement. Now just substitute the dimensions. Current has a dimension of amperes. Okay, so ampere square. Time is time, so time square. And then force is Newton, which is kg meter per second square. So kg is mass raised to 1, and then meter, which is length raised to 1, second square, so t raised to minus 2, and this displacement is again length. So just do the math and you'll get it. Is it C? Everybody is getting C option. Just check this out. M raised to minus 1, length raised to minus 2, time raised to plus 4, and ampere square. Yes, it looks like option C. I hope it is option C. Yes, it is option C. You guys are correct. Perfect. Very good. You guys are fast. Moving on. There is a sphere of radius r. It is charged to potential V. Then the charge is proportional to this. Many students are going to make a mistake. Okay. Be careful. This can be a tricky. This is a point where you're going to lose marks. Let's see how many of you can get this. Sir, in C option, it should be t raised to minus 4. No, Amar, that's wrong. It should be t raised to plus 4. It's correct. The t raised to minus 2 was below. When you take it on the top, it will become t raised to plus 2. T raised to plus 2 into t raised to plus 2 will become t raised to 4. So it is correct. Perfect it was. Okay. Like I said, many of you are going to be wrong in this. Yeah, I can see that. So many students are wrong in this. Okay. So what do you do over here? See, okay, I'll first show you the answer. So let me break the suspense. The answer is C, by the way. Now, why is the answer C? So here is the thing. Q is basically CV. So if you have a sphere and if it is charged, it also has capacitance and the charge on it is C into V. Now capacitance is 4 pi epsilon naught R. Now from where did you get this? From the passage. It was just given directly in the passage into voltage. Now do you see that clearly charge is proportional to radius, it is also proportional to voltage. So basically answer is both of them. Correcto. Very good. Very few people got it. Very good Arpita, Khushi. Vimla, samajh mein aaya C kaise? Got it? Yes. Very good Selvendran. Very good. Excellent. Moving ahead to the next question. Oh, we have current electricity. Chalo, time to open up NCERT now. Everybody open up NCERT. I know you guys are having fun. Let's go to NCERT quickly. Let's go to the third chapter. See, we have already completed 2 chapters. Imagine we are going to complete all the chapters and you will be like, sir, now I am confident. And you are going to feel that when you read through NCERT and everything will look very, very familiar. because we are all studying as a group, we are all studying as warrior community, we are studying this as Vedans. So we are going to rock it. Don't worry, my warriors. Let's do this. Go to current electricity. Quickly open up, the NCRT. Let's go to what is important right now and start underlining with me. Okay, what is electric current? This is okay. Here we have it. Okay. Okay. This. Okay, over here. Yeah. So, what is the definition of current? And the current that flows across a cross section is the amount of charge that flows per unit time. Okay, this is very important. And going ahead over here, this SI unit, which is the unit of current, remember this is a fundamental unit. Okay, charge is not fundamental, current is fundamental unit. Okay, so it is defined as, how much charge which flows per unit time. It can be defined from, in fact, also the formula of force between two parallel wires which carry current and how much is the force between them. So from force you actually define the current, so it's okay. Anyways, now going ahead over here, this and all electric current and conductors, let's all go ahead. This all just tells you what is the mechanism. So the whole idea of this over here is that if electrons go in this direction, the current actually goes in this direction, because the current is the flow of positive charges, okay, by conventional current. That's the whole gist of this entire paragraph. That's all. Okay, now over here, Ohm's law, of course, V is proportional to current. This is only for ohmic devices only, not for anything else. There are devices where voltage is not proportional to current. You will see that in semiconductors in term 2. Okay, but this is not true for everything. And R is the resistance. The SI unit is ohm. Fine, all of this. You know this from before. Now here, how does resistance depend on length and all of that? So we have a formula right over here. Okay, resistance is directly proportional to length and inversely proportional to area for any given conductor. This rho is called as resistivity, and it only depends on the material. Again, very important, depends on material. And remember, 1 by rho is also called as conductivity. What is it called? It is called as conductivity. Very, very important. Chalo, let's go down below more. Okay, everybody, I think following it till here. Yes, rho L by A. Yes. Okay, I have just zoomed it a little bit more. Now, this is another important formula. E is equal to rho J. Very, very important. But you can also write it in vector form if you want it. So let me just in fact highlight that vector equation. That's more important. E is equal to rho J. And J is also equal to sigma E. Remember, I just told you conductivity is 1 by resistivity. So don't remember both. Remember this one. This is important, because if you remember this, you will get this. I'll tell you how. See, just like V is equal to IR, voltage, what is the quantity which is similar to voltage? Voltage per unit length, that is called field. dV by dr is field. Instead of current, you have J. Now what is this J? J is current density, current per unit area. Specific resistance is resistivity. So that's how you can remember it. E is equal to rho J. Okay? And if you take rho onto the other side, 1 by rho will become sigma. That's all that is there. I think the definition of current density is also over here. Current per unit area, normal to the current, I by A, is called as current density and denoted by the symbol J. Very, very important. Okay, so this is also important, the definition of current density. Very good. Okay, cool. Let's go ahead. Let's go ahead. Definitely, Isha Khan, you're going to score it. Don't worry. All right. Now, the derivation of drift speed and all of that is there. Ignore that. Just remember the final formula over here. Where do we have it? Yes, right over here. Keep this in mind. The current density is NE square divided by mass into that average time of collision into the field. Very important. What is this N? This N is basically number of charge carriers per unit time. It has been defined somewhere on the top. Okay, where is it? Okay, there we go. Yes, here N is the number of free charge carriers per unit volume of that metal, and it completely depends on that metal. That's all. Okay, what is drift speed? Drift speed is the average speed of all the electrons, okay, which flows through a conductor when you apply some voltage difference. So the what is the definition of drift speed, etc., is mentioned here, is the average speed at which electrons move. That's mentioned here. What is N is mentioned here. That's all you need to know. And this is one thing. Okay, now you can also rearrange that same equation and you can get this, but if you want, I'll tell you a better equation as well apart from this particular equation. You can also remember I is equal to NVDR. This is also a very important equation which will help you, and the reason why I'm telling you about this equation is because it's easy to remember. NVIDIA, it's a graphics card company, so NVIDIA, current is NVIDIA, remember that, it will help you a lot. Very good. So more than this formula, this is important. You can just rearrange this and you can still get that or even this, one and the same thing. Very good. Move down. Let's move down. Okay, perfect, perfect. Go down, go down. Mobility, yes. Here, in fact, whatever I was just telling you, I is equal to NVIDIA, it's right going to be over here. And what is the definition of mobility? Mobility is, how much is the drift speed per electric field. So this is the formula for mobility. You should know this. Speed per electric field, how much mobile it is, how much is the speed per unit electric field. Okay, all of this is fine. Okay, move down. Limitations of Ohm's law. This is what I was talking about. This was for non-ohmic devices. V is not proportional to current. The V and I depends on the sign of V. So this will come in semiconductors, but these are all basically non-ohmic devices. Non-ohmic devices. Keep this in mind. Okay, perfect. Let's go down then. All right. Resistivity of various materials. This topic, most of it is removed. This is a table. This table is not important. You are not going to sit and by heart these values. Okay. This is not so important. This has all been deleted. Okay. Even this color coding is not there. But yes, temperature dependence of resistance is there. And this is the formula that you are going to remember. Resistivity is rho naught 1 plus alpha delta T. Very, very important. What is this alpha? Alpha is basically the coefficient of thermal resistivity, and T naught is basically the reference temperature. That's all you need to remember here. Going down. Okay. Oh, by the way, I forgot to tell you, alpha can be positive, negative, or even 0. 0 means it does not change. If it can be positive or even negative. Positive means resistance increases with temperature. Negative means resistance decreases with temperature. Okay, so both the things are possible. Okay, all this is not so important. Go down. Oh, there is one thing which you can remember though, right over here, the resistivity, which is 1 by sigma. This was also there before. This was done before. So it's the same thing. It was the same thing done before. All right, go down. Go down, go down. Electrical energy and power. Yes. Over here, yeah, these are your standard formulas. The power loss across a resistor is I square R or V square by R. Which one will you use when? See what is constant, see what is variable, decide accordingly. If current is same, that is in series, then use I squared R because it will be easy. If they are in parallel, then voltage will be same. So generally, I'm not giving it as a rule, generally in series, current, because it is same, so use I squared R, it will be helpful. And in parallel circuits, voltage is basically same, so generally use V square by R. Just keep this in mind. But things can change depending on what is given and not given also. Okay, now all this is fine. This is not so important. Resistors in series and parallel, everybody knows, that's standard. This is resistors in series, and obviously this is resistors in parallel. This you have been studying right from 10th standard. You know this. Okay, so I'm not spending so much time there. Go down a little bit. Batteries, cells. Okay, the definition of EMF, the difference between the voltages, EMF is right over here. Okay, EMF is actually a voltage difference, not a force. Very important. The name can be misguiding. However, it is used because of historical reasons, because people used to believe there is a force which causes the electrons to move. That's the reason for that, but you don't have to worry about it so much, but something to remember. Okay, now this is again interesting cases. There are 2-3 cases, like when the resistance is infinite, basically the current is zero, no current, when there is no current, okay, or basically open circuit, then the voltage across the battery is the EMF. Very important, the voltage is the EMF. So when the current is zero, but when it is discharging, then the voltage will be E minus IR. You can see that I is there. Only when I is 0, E is V, not otherwise. Be careful. Okay, those are the 2 important cases that you should know. And yeah, that is fine. Okay, great. One more thing, there is this situation for discharging, but what if it was charging? So if it was charging, that means there is this battery and the current is coming inside of it, not outside of it, then voltage will be E plus IR, not minus. That's something which you can keep this in mind. And the 4th case is right over here, the maximum current. Okay, the maximum current which can be taken out of a battery is when external load is 0. So basically you just have that battery with internal resistance and it's just a wire. So this will be max current, but most likely it will burn because lot of heat will be produced, so much current will go because internal resistance is generally very small. So that's what they have mentioned. Okay. Now this can be there for case study. So whatever paragraph you see over here may be important for case study. So you can read through this. There can be questions based on this. So that's why I'm marking this over here. So charges in clouds, moving down, cells in series and parallel, 2 or 3 batteries connected in series or parallel, then what happens? Okay, this is what happens. There you have it. This is for series. So you have multiple batteries connected like this. You can convert them into one single battery. Equivalent EMF will add, equivalent resistance will also add. That's it. Okay, perfect. Okay, there we go. To the next part, when they are in parallel. So when they are in parallel, then what happens? Where is it? It's right over here. You can see this. Equivalent EMF is E1 R2 plus E2 R1 by R1 plus R2, and this is like this. So basically if you have two batteries in parallel, you can convert them into one single battery. These are the formulas, very, very important. And an easy way to remember this formula, I'll tell you. The easy way is E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2. So if you take the LCM now, you will exactly get this. So E1 by R1 plus E2 by R2 upon 1 by R1 plus 1 by R2. R1 R2 cancels and you will get the same thing. So easy way to remember. Okay, perfect. Now all these are fine. Going ahead, Kirchhoff's law. Kirchhoff's law, yes, it's based on energy conservation, conservative forces. Okay, so where is it? Yeah, let's go down. Okay, junction rule, right over here. So mainly over here, just keep this in mind, the sum of voltages across a loop, that's what you should remember, is 0. You don't have to remember the theory. If you remember the formula, that's important because you'll get questions on this. And this is the junction rule. So the sum of currents at a junction will be 0. If you add in and out currents, it will be 0. That's it. Okay. Now it's mainly all about applications. Now I'll give you some important points that you can remember. A lot of people get confused with the signs. So I'll tell you, for applying Kirchhoff's voltage loop law, what are the signs or how should you take care of the signs? I'll just put it over here. So you will never face any difficulty. Imagine you have a battery and let's say you are going from, here to here, it will be plus E. But if you go from here to here, then it will be minus E. Keep this in mind, because high to low. Similarly, for example, there is a resistor. Okay, there is a resistor and there is current flowing like this. Then when you go opposite to the current, it is plus IR, but when you plus IR, and when you go in the direction of the current, then it is minus IR. Keep this in mind. If you know this, that's it, your job is done. That's it. Okay, very, very important. Cool. Let's go ahead. Remember, CBSE board is an objective examination. We don't have derivations now. We don't have to write any theory. So that's the best part. We have to focus more on the problem side of it. My approach would have been very different if it was, a written exam where you have to write all the theory, you have to give reasons. Yeah, then so many things would change. The best part is it's just a formula based question. Exam. Okay, now balancing condition, obviously very important. Again, let me just mark it over here. Okay, so balancing condition. This is the condition for balancing the Wheatstone's bridge. Very important. So this is the Wheatstone's bridge diagram, which you cannot forget. The current is 0 when it is balanced. There is no deflection right over here. Okay, now going down, meter bridge. This is just nothing but Wheatstone at the end of the day. This is nothing but Wheatstone. You will be able to see there are resistors here, here. There are 4 resistors actually speaking in a meter bridge. So it makes it a Wheatstone's bridge itself. And this is the formula. As such, in the syllabus they have mentioned only qualitative part is there, quantitative is not there. But still, you never know. It's better to remember this. Let me tell you an easy way to remember. Okay, RS and this one. So I'll tell you what you should do. This is, let's say R, this is X, and this is another resistor, this is another resistor, and this is your galvanometer, which shows no deflection. This is 0. This one is L1, this one is 100 minus L1. That's it. This by this is this by this. That's all. Is that clear? Yeah. This is something which you can remember from Wheatstone's perspective. Don't try to remember this formula as such. Resistance S, L1, 100 minus L1. How did I get to this diagram? From here, look at this diagram over here. This is one resistor, this is one resistor, there is a galvanometer. This is one resistor, this is one resistor. So if you remember this concept, you will get the problems very easily. Perfect? Okay. Now going ahead, yeah, we'll go to potentiometer. So potentiometer may, yep. So where is it? Yeah, this is one of the application. Okay, comparing EMFs. So for comparing EMFs, you need to remember this. Comparing EMF, and here, okay, yeah, yes, potential gradient. Also very important. Yes, the potential, why is the potential drop per unit length? It is also called as potential gradient, very important. So that's voltage per unit length. Okay, and if you go down, basically you have that resistance wire, and on that wire, between the two ends you have some voltage. So this phi gives you voltage difference per unit length. So if you take a particular section of the wire, how much is the voltage? So that can be calculated easily using this formula. As simple as that. Very good. Chalo, let's go down over here. Oops. Okay, let's go down. Okay, great. Nothing great over here. This is another important formula when you use potentiometer to find internal resistance of a cell. But as such, again they have mentioned that qualitative analysis only. As such, they have not told कि formula based questions will come. So my guess is if potentiometer applications come, they should come in case studies, or they should not come in assertion reason or even in MCQs. Okay, so that's what my guess is. But You never know, but still that's why I've told you to remember it. Okay, again we come back to summary. So remember, all the summary points are important after every chapter. Okay, so go through this. Most of the things are there already marked. This is not important, ignore this. Directly go to points to ponder. Directly go to points to ponder. This is again important. So that's all you need to do from this chapter. Okay, everyone fine? So these are the 3 things that you need to do. Okay, I'll just save this. I'll just save this as well and save this as well, because you will need it later on. Ready to do some questions? Let's do some questions. Perfect. Yep. Yeah. Chalo, let's move to questions. Here is the first question coming up on your screen. There is a balanced condition, and if the galvanometer and the voltage source are interchanged, then the balancing condition remains the same. The balancing condition of a Wheatstone's bridge does not depend on the value of the resistance. Interesting. So basically you have a Wheatstone and it is balanced. Let me just draw the resistances. Meanwhile, you can just solve the problem quickly. So this is your galvanometer and this is your voltage source. Let's see if you have understood the question. In a balanced condition, you can interchange the galvanometer as well as the voltage source. So what it means is you can still have those resistances, but here you have the voltage now. Here you have that resistance, again one resistance, and now here you have that galvanometer. Do you think both these are same? Okay, what do you think? Are both of these conditions same or different? Let's see. Actually speaking, I'll tell you what, if you visualize this, you can take this galvanometer out like that, and this battery you can put it between them. You can visualize it. You can put the battery between these 2 points, and galvanometer you can put it from outside, and you turn the diagram, it is actually the same thing. So yes, so when you interchange it, it is the same. It does not get affected. Balancing condition does not depend on the value of resistance. What nonsense. It always depends. R1 by R2 is equal to R3 by R4, whatever it is. So it depends. So reason is false. Hence, option C is correct. Perfecto. Yep. Yeah, color coding is not there. Color coding is not there. Yep. Okay, moving on to the next one. Potentiometer is used to measure the EMF of a cell. Potentiometer is preferred over a voltmeter to measure the EMF of a cell because it does not draw any net current from the cell. What do you suggest about this? Islamic media, you want a sign convention for capacitors? Don't worry, I'll give it to you for capacitors also. So here it is. So for capacitor, okay, I can just put it right over here. So if, for example, this is the positive plate, this is the negative plate, this is positive plate, this is negative plate, then if you go from here to here, it is minus because high to low, and from here to here it is plus. And remember, Q is equal to CV, correct? So voltage is Q by C. So hence, when you're going down, it will be negative of Q by C, and when you're going up, it will be positive of Q by C. That's how the sign convention for capacitor is. That's all. Okay, so what about this? NCRT plus MCQ questions, both are needed, Roman. All right, so many of you are saying option A, and you guys are correct. It is measured to, it is used to measure the EMF of a cell, and the reason is it does not draw any current. So when you have a potentiometer, something like this, this is your potentiometer circuit, this is your potentiometer wire, this is that potentiometer wire, and you take a battery and then you take a galvanometer and you connect it via jockey right over here between these 2 points. At balance condition, the current is 0. If the current is 0, it does not take any current inside this branch. So it measures the battery's EMF accurately, because I don't know if you remember this, voltage is E minus IR. So if I is 0, V is equal to E. So you will not get any error in the EMF. The moment any current flows in the battery and then you measure the voltage, you are going to get some IR error in that measurement. So keep this in mind. Is that clear? Moving on to the next question. Perfecto. It can be used to compare EMF. It can also be used to measure EMFs on there. Yeah. Okay. Both uses are there. So one application is, yes, you can use it for comparing EMF E1 by E2, but if you see that part, E1 will be potential gradient into the balancing length. So that's what it comes out to be. Yes, let's move ahead. Electric appliance with metal body has 3 connectors, but a bulb has 2 connectors. 3-pin reduces chances of electric shock. What do you guys say? Yep, yes, Vrishti, it is used for internal resistance too. Like I mentioned, there was a formula just which I highlighted it right over there. Okay, very good. Many of you are saying B, some of you are saying A. Looks like you are confused. What do you think? Yes, Dark, you are going to get the PDF. Yes, you are going to get the entire PDF, don't worry. But point is not the PDF, the point is attending these sessions live, because anybody can get the PDF. The point is to solve these questions in a live class with discussion. You have that mood. Well, the correct answer is actually A. Well, see, I'll tell you a simple fact. When you see a 3-pin connector, okay, one is live, one is neutral, okay, you don't have to worry about it so much, okay. Just understand that there is these 2 pins which are very important, because let's say you have some motor or something which is connected to your fan, bulb, whatever. These 2 points are connected to your motor, bulb, whatever you want. This 3rd pin, okay, this 3rd pin is a special pin. It is connected to the casing. So what happens is, behind the scenes, this wire is directly connected to the earth. So if there is any leakage, of current, then what happens that when you touch the body of the device or that appliance, you will get shock. So instead, all that current is made to flow via this path into the ground, and even if there is a person who touches that particular metallic body, nothing will go through it. All the current will go through the ground pin. So this ground pin is very, very important. Okay, so 3-pin reduces the chances of shocks. Perfect, very good, excellent. Moving ahead to the next one. The drift speed of a metallic wire will decrease if the temperature of the wire increases. On increasing the temperature, conductance of the wire decreases. What do you say about it? Think about it. Think about it. Yes, it is called as earthing. Perfect, I know. So 2-pin is harmful. Yes, it is harmful, or rather, I won't say it is harmful. I would say it has less protection. Sometimes you don't need a 3-pin when everything is plastic body. So if everything is a plastic body, then you don't need it. It's not like it's harmful. It's just that it's not needed. Okay, cool. So many of you are saying A, some of you are saying D. Well, actually the correct answer is B. Oops, looks like many of you made a mistake. And let's see why. Drift speed will decrease if temperature increases. If temperature increases, resistance increases. But, if voltage is constant and voltage is I into R, and if resistance increases, the product should remain constant, so current will decrease. If current decreases, the drift speed will decrease, because current is NVIDIA. Current goes down, small current, less speed. The electrons will flow at lesser speed. So here it says the drift velocity will decrease if the temperature is increased. Cool, this is correct. On increasing the temperature, the conductance will decrease. Well, resistance increases, that means resistivity increases, that means conductivity decreases. So conductivity will definitely decrease. But decreasing conductivity has no reason, it does not explain it. You have to explain it via this process. You cannot directly say because this decreases, this increases, or this decreases. So it doesn't make sense. It's not explaining it properly. Okay, there is no proper explanation. So that's why reason is not complete, or it's not the correct explanation. Is that clear? Yes. Hello Saksham, welcome aboard. All those of you are joining in new. Today we are doing the marathon session for CBSE. I've already done the 2 chapters. We are almost nearing the end of the 3rd chapter. Let's see whether you can solve the next question coming up on your screen. There are 200-watt bulbs which glow with more brightness than 100-watt bulb. A 100-watt bulb has more resistance than a 200-watt bulb. Okay, what do you think about this? Yes, it is indirect explanation. So for study, remember, whenever you have assertion, reason, explanations, the explanation should be the direct explanation. Only then you can mark it. else it's not the complete or correct explanation. Yeah, break is going to come now. Okay, come on my warriors, figure this out. 200 watt bulb glows with more brightness than 100 watt bulb. What do you guys say? Obviously, yaar, more wattage means more power will be consumed. That means more light. That obviously makes sense. So 200 will grow obviously higher. You would have seen that when you go to electrical shop, you buy a higher wattage bulb, that means it glows brighter. A 100 watt bulb has more resistance. Well, power is V square by R. Remember, V is constant. So 100 watt bulb has less power, so more resistance. Yes, this is also correct. But how is this related to this? It does not even explain it. So it's not the correct explanation. It's not the correct explanation. Both are correct. But how is it explaining? Did it explain? No. Saksham, well, it will be definitely useful for you maybe for next year, but for now, maybe no. Yeah. So be careful. A lot of students get confused between A and B. It should explain it. It should satisfy it directly. Else you do not mark it. Okay. Don't do that. Okay. The length of the conductor is doubled. Velocity, the drift becomes half. At constant voltage, drift velocity is inversely proportional to the length of the conductor. Anjali, I took your name too. Okay, chalo, come on. Post up more answers. I think I'll take your name more often then. Okay, Pooja saying B. Make it unique saying A. But power is also I square R. Yes, Miss Smiley. So remember, when you connect appliances, is current constant or voltage constant? Voltage is constant because you connected all appliances in parallel. Did I not give you that chart? That when you connect devices in parallel, voltage is constant. So most likely you are going to use V square by R. So whatever is constant, use that formula. Current will be different. Understood? Yeah, correct Akshat. The same reason I just told you. Okay, let's see if you can get this. All right, the length of the conductor is doubled, the drift speed. Option A is correct, and I'll tell you how. Okay, the length is doubled. Now resistance is rho L by A. So if you double the length, then the resistance will also be doubled. Now because it's given voltage is constant, so since V is equal to IR, so if resistance is doubled, then because voltage is constant, current will be made half times. Current will become half. Next, current is equal to NVIDIA. I just gave this to you. So if current becomes half times, N is same, E same, A same, so drift speed should also become half times. So indirectly, if you see here, the length and drift speed are inversely proportional. That's how they are related. They are related. The length of the conductor is doubled, the drift speed will become half. At constant potential difference, this is the derivation for that. So when voltage is constant, when you increase the length, then you see that the drift speed is inversely proportional to that. So this is the missing link which has been correctly put over here. It's already been put over here, so option A is correct. Got it, my warriors? Perfecto? Yes. Great. Moving on to the next one. This is the last passage, and then we'll break out. We'll have a small teeny mini break, and then we'll again return for the remaining chapters. Okay. What does this symbol tell you? Take a screenshot. Come on, take a screenshot, and then we are going to break out. Come on, my warriors, do this quickly. Take a screenshot. If you're done, please put up a heart quickly so that I know you have taken the screenshot. This is based on potentiometer as a voltmeter. Potentiometer as a voltmeter. Come on, let's do the questions. Okay, done. Very good. You have taken the screenshot, looks like it. Okay, read it quickly if you want to. I can see all the hearts coming in, and here is the first question. Which of the following is true about the potentiometer? Come on, solve this. Which of the following is true about the potentiometer? It is having very less sensitivity, it measures the EMF very accurately, it is based on deflection method, or none of these. Come on. Very good. Option B, perfect. Moving ahead to the next one. It behaves as a very accurate voltmeter because the current which it draws is zero, because it is based on null deflection. Hence, it's a very accurate device. The current is this much. Potentiometer wire's length is 4 centimeter. resistance is 4 ohm. What is the potential gradient of the potentiometer wire? So basically what it says is you have a potentiometer wire which is nothing but a resistance. Resistance is 4 ohm, the current is 1 milliampere and the length is 4 centimeter. Question is voltage gradient. Come on my warriors, let's do this. Potential gradient. Potential gradient means voltage per unit length. Voltage is current into resistance. Current is 1 milliampere, so 10 to the power minus 3. Resistance, what is the resistance? 4. What is the length? 4. So centimeters, so 10 to the power minus 2. So 4 goes, this will become 10 to the power minus 1, which is 0.1 volt per meter. So is it there? Yes it is, option A. Perfecto, perfecto. No, it is not C, it is option A. As simple as that, I just did it. Oh, who is it? Burudin Miyaji. Okay, I just took your name, bacha. Okay, sometimes, you know, the names can get skipped. Don't mind it, okay, sometimes. Burhanuddin. Okay, I hope I'm pronouncing your name properly, Burhanuddin. Okay, very good, Burhanuddin. Let's go to the next question. Sensitivity of a potentiometer can be increased by which of the following? Only one is correct. Decreasing, increasing, decreasing, increasing. Gradient, current. What will your answer be? Live and neutral, basically you will understand it when you study phasors and phase. So neutral is the point where all the three phases of voltage cancel out each other, and live is one of the phase wire of that 3 wires that you have. So that's what it is. More technical. You will learn it when you take electrical. Okay, many of you are confused between A and B. Let me tell you, many of you have made a mistake. So the correct answer is actually A, decreasing the potential gradient. See, when you travel some distance and you get more voltage difference, that means 4 volts per meter as compared to 2 volts per meter, this is not accurate. Reason is, even if, see, that potentiometer wire is there, you take this circuit, something is there over here, this is your galvanometer and this is your jockey. If you move this slightly, then the voltage will change by a large amount. You will have more chances of error. Here you have more room for, adjustment. The voltage changes slowly. You put it here, then you put it here, then you put it here. So it changes slowly. So the galvanometer will also show deflections in a very smooth manner. In the case of higher voltage per unit meter, then a small change in the jockey position will affect the galvanometer reading significantly. So it won't be a very good or a smooth reading. So for smoother readings, you should have lower voltage sensitivities. Keep this in mind. Okay, moving to the next one. Correcto. Now, a potentiometer is an accurate and versatile device to make electrical measurements of EMF because this method involves gradients, condition, combination, cells. Come on, look at this. So why not C for the previous one? Current might not necessarily decrease the voltage gradient. So you might change the current, but what about the resistance and the length? So that's the problem. That's why C was not correct. Okay, many of you are confused between B and C. Well, the correct answer is B actually. There is no Menti code. This is not a Menti. This is a live just session with quizzes and students have to answer in the chat box. Okay, so the condition for no current flowing through the galvanometer, basically null deflection. Remember one thing, null deflection methods are always very, very accurate because V is E minus IR. So if I is 0, V is just E. No error. There is no error in this. So that's why it is very accurate. Keep this in mind. Okay. Next, there is a potentiometer experiment. Balancing length is 8 meter when both cells are in series helping each other. But when they are opposing each other, the new length is 4 meter. What is E1 by E2? Comparing EMFs. Remember comparing EMFs method? Let's do this. Yeah, comparing the EMFs. Let's see if you can get the question's answer within 30-40 seconds. You should not take it more than that. No, Balkavi, it is visible, but sometimes probably I might not be able to see your comment and solve your doubt. Maybe you can put it after the session ends or ping me on my Instagram handle, Shreyas_Vedantu. That's my Instagram handle out there. You can follow me and then ask me questions. Well, when they are helping each other, okay, then it will be E1 plus E2, and when they are basically opposing each other, it will be E1 minus E2, and this by this will be L1 by L2. L1 is 8, L2 is 4, so this will be 2 by 1. So this is E1 plus E2, and this is E1 minus E2. Use componendo dividendo. If you use componendo dividendo property, this will become E1 by E2 will be 2 plus 1 divided by 2 minus 1, which is nothing but 3 by 1. So 3 by 1, where is it? Option D. Done, done, done. Yeah? Cool? Very good. Very good. Very good. 3:1. You can also even cross multiply if you want. Just cross multiply this. You will still get the same answer, but it will be 1 step or 2 steps more. Perfect. Time for a break. Time for a break. So let's put a timer out here. All right. And we are going to have a short break for, let's say, 15 minutes. Okay. The break time starts now. See you. We are going to start with magnetism after this. All right. So magnetism and all of that is going to start after this. Welcome, welcome, welcome. I hope you can see me and hear me loud and clear. Welcome aboard. Yes, let's begin our session. Yep. So the break time is over. By the way, you're going to have one more break after some more time. Okay. So let me just cover 2 more chapters and then again a small break just before we wind up the big marathon session. So those of you who are joining in a little bit late, I have just completed electrostatics, Gauss's law, current, electricity and capacitors. Before the break, we are revising via NCERT, underlining it, revising it, then going to assertion reason questions, and then we are also solving case study based questions. So it's a marathon session for term 1. If you want to score full marks, then you need to be here. You are at the right place. And yes, if you have forgotten to smash the like button, please do that right now. And thank you for all the love, thank you for all the affection, and thank you for hitting the subscribe button. Okay, so let's continue with the session. All right, so there we are. Okay, so time to open up NCERT, moving charges and magnetism. It's a short and sweet chapter. Both the chapters ahead are short and sweet. So let's open up NCERT. Come on, my warriors, let's do this. Okay, let's go here. 1 second. 1 second, let me just open up NCERT just for you. All right, all right. 1 minute, there we go. Okay, so we have NCERT right over here. Don't worry, I'm going to zoom it just for you. All right, cool. Don't worry, Vajithari, Sakraj, I'm here to help you only. Thank you, Saksham. And yes, MS Smiley, the break is over. Thank you, Arpita, for the hearts. Very good, Ankita. Very good, Amar. Thank you for the warm welcome. Thank you, Satvik. On time. Yes, I'm always on time. Moving on. Introduction, skip, move ahead. Field due to long straight wire carrying currents, how does it look like? That is all standard. These are all dot and cross notations. That's okay. Moving ahead. Okay, so the electric field is this much, force is this much. This is all revision, so you don't even have to do this. Just move ahead, move ahead. Magnetic fields force, this is what you need. See, this is QE. You have already done this, force between 2 charges, so don't have to waste your time there. Lorentz force, electric force plus magnetic force. This is what is important. So this is what I'm going to highlight it just for you. So there we go. So the force due to electric and magnetic fields is given by charge into electric field plus V cross B. Essentially, force due to magnetic field is Q V cross B. So if velocity is here and magnetic field is here, then the force is going to be perpendicular to B as well as velocity. So this is the angle between them. That's how it is. Force is perpendicular to B as well as velocity. Keep this in mind. Okay, it is called as a Lorentz force. You already studied this in detail. All this, okay, fine. Now, force on a negative charge is opposite to that on positive charge. This is like very obvious here. I mean, come on, because Q is there. Q can have positive or negative sign. That's obvious. And it's a vector product, that is also understood. Okay, so when does the force vanish? If force is 0, then V cross B is 0, then velocity is parallel to magnetic field. That means theta is 0 degrees. So velocity and magnetic field both are parallel. In those cases, you will see that the force will be 0. Yes, there are other cases also, like velocity is itself 0, charge itself is 0, B itself is 0. Those are like obvious. But special cases will be when V is parallel or even anti-parallel. 0 degrees or even 180 degrees will also do. 180 degrees will also be okay, because sine of 180 is also 0. Alright. So moving ahead, don't worry guys, irrespective of how the CBSE paper is going to come, we are going to prepare you for the worst. We are covering NCERT today, tomorrow formulas and good questions, and then day after tomorrow sure short sessions. The session starts at 11 o'clock, so don't miss that particular time. Alright, moving down. Okay, dimensions and all of that, this is fine. Now this is very important. Force acting on a wire, IL cross B. So this is the force acting on a wire which carries current. So if you have a wire which carries current, the magnetic field is over here, the angle between them is like this. This is the force acting on it, IL cross B. That's it. This is the force on the wire carrying current. Moving down, now over here, permittivity, permeability, that's okay. Here they have given this paragraph which is again one interesting paragraph. I think you should just go ahead and read it once just for the sake of case study. That's it. So just please go ahead and read this. It will hardly take you 5 minutes, not more than that. The gist of this is, just like you have epsilon of a medium is epsilon naught into K, which is your dielectric constant. Same way mu of a medium for magnetism is nothing but, so mu of a medium is mu naught into relative permeability. So this is called as relative permeability. So that is something which you should know. This is for free space, which is 4 pi into 10 to the power minus 7. That's for free space. Okay, I have put it over here. It will be available in the PDF later on. Go down, motion in a magnetic field. I didn't see that topic in your CBSE portions, so I think you should give it a miss, but it might come in your, oh sorry, my bad. Motion of a charged particle is there. EMI mein motional EMF is different. My bad, so sorry. Okay, this formula R is equal to mv by qb, which is also p by qb. This is also very important, momentum by qb. And yes, the time period, you can remember this formula, or you can also remember 2 pi m by qb, one and the same thing. This is also very important, and important part is it is independent. It is independent of speed. That's very important. Then what happens when you throw it at an angle? Then it describes a helical path. The distance moved along the field in one rotation is called as the pitch. The definition of pitch is there, and the formula for pitch is also given. You should know this. 2 pi m v by qb. Okay, so that formula which is there, that will have the parallel component of the velocity. What it means is that if you throw the charged particle at an angle with the field, then the parallel component will remain constant, but the perpendicular component will make sure that it goes in a circular path. So because of this perpendicular component, it will go in a circular path of some radius. Okay, so only that perpendicular component is useful. Remember, on parallel velocities, the force on due to magnetic field is 0. So don't worry about it. So going ahead, next, let's see what do we have. Go down. Helical motion of a charged particle, yes, very important for case study point of view. So again, case study ke liye, this is very, very useful. Please study this. Okay, cool. I'm putting it right over here. Then, yeah, motion of particles in electric as well as magnetic fields. This is again a very important formula. V is E by B. This is also useful in velocity selector. Okay, this is the application, and this is also called as crossed field. Crossed field meaning you have electric field, you have magnetic field, and you have velocity. All three are perpendicular to each other, but still the velocity remains unchanged. This velocity remains constant. When does it remain constant? When this condition is obeyed. When V is E by B, the force due to electric and magnetic field will cancel. The net force is 0. Keep this in mind. And that's when, you know, the charged particle goes in a straight line without any net force. If the velocity is slightly more, it deflects on one side. If velocity is slightly less, it deflects on the other side. That's why it is used in velocity selector. Keep this in mind. Okay, let's get going to the next one. Cyclotron is deleted, that's why I have marked it in red, so ignore that. Okay, so that's all that is there. Acceleration in India not needed, guys. Okay, Biot-Savart's law. Yep, the statement of Biot-Savart's law, that's what you need over here. So the magnitude of the field due to an element, this diagram is important, okay, is given by mu naught by 4 pi I dl. What is I and dl? Current into the length into sine theta. What is theta? Theta is the angle between the length and the position vector divided by r square. That is the formula for finding the field due to any element. Due to element. Okay, let me just put it over here. So it's a constant. The magnitude of this field is given by this particular formula, and I've already told you what is the value of mu naught by 4 pi. So mu naught is 4 pi into 10 to the power minus 7. It's already mentioned before also, but still I'm highlighting it right over here. Okay, now all this is fine. Okay, so again you can use superposition principle of superposition. That means vector addition of field. That's all that it means. Vector addition of field is valid. You can use it. Electrostatic field is produced by a scalar source, namely the charge. Same way it is produced by vector source. Ideal. That's okay. You don't have to remember it so much. Okay. This and all is fine. This and all is fine. Special cases, it's okay. You don't have to remember this. This is okay. You can skip this. Okay, because these are all just special conditions. Theta is equal to 0, obviously. See, I'll tell you what this means over here. Imagine if you have a wire which carries current, okay, like this, and you are also here. If you are at this point, that means my R vector will be here, my DL vector will be here, my DL and R, the angle between them will be 0. So therefore, the field will also be 0. So if you are on the axis of the wire, then the field will be 0. That's what this statement means. So that's what this paragraph is all about. So you can skip this part, it is obvious. Let's move ahead. Force on a on a coil. Yes, let's go to the forces on the coil. Let's go down. And before that, I think we need to go to field due to a coil. Yes, this is that formula. Magnetic field due to a coil which carries current, and this is the special case. This is on the axis and this is at the center when x is equal to 0. So if you put x equals to 0, you will get this. What are these two formulas? See, if you have a current carrying loop and you are on the axis, due to this current carrying loop, what will be the magnetic field due to this loop on the axis? That's the first formula. But if you are at the center of the coil, then what is the magnetic field? So that's why you have two formulas. But let me tell you, if you remember this, you automatically remember this. Because if you put x equals to 0 and if you solve this, you will get exactly this equation. Fair enough? Everyone? Cool? Alright. Let's move ahead. And how does the field diagram look like? This is very important. You cannot miss this. Okay, move ahead. This example is very important. So for an arc, so due to an arc, how to calculate the field? So that is something which you can look forward to in this particular example. Now, Ampere's loop law. Cyclic integral B dot dl is mu naught I. Very important. The sum of all the dot products of magnetic field with the length is mu naught into I. Now what does this mean? I'll tell you over here. See, if you have a current, if you have another current carrying wire, again another current, again another current. If these are currents I1, I2, I3, I4, and let's say for example, you go around these currents, you cover a path like this, then at every point when you're traveling, you're displacing by some small amounts, let's say dl, and at every point, let's say there is magnetic field B. So if you do the dot product of B with dl and you keep doing that addition, add that B dot dl, B dot dl, so you will basically integrate it and you come back to the same point. That's why cyclic. That is equal to mu naught into whatever current is only inside of this loop. What current is inside? This is inside, this is inside, this is inside. This should not be counted. That's what Ampere's loop law is. Cool? Great. Obviously, you'll have to study after this session. Just this session won't be enough. Whatever I underline and give you, you are going to revise it after the session. You are going to go through the problems wherever you made mistakes or wherever you thought you got it wrong or you did not get it correct the first time and all of that. So that's what you need to do. Okay. Moving ahead to the next one, Ampere's loop law. That's what it is. Okay. This and all is fine. Yeah. So this is magnetic field due to a straight wire. This is something which you can remember. So you have a wire which carries current and you have field around it. So magnetic field lines are around it like this. So at a distance r, what is the magnetic field? This is the formula. This is something which you should keep in mind. Going ahead. Okay, so the field direction is circular. All these are basics, but still if you want to go through, then you can go through. So I'm just circling this, just do this point and this point. I'm not marking it as important because this is just based on Orsted's experiment, which you already have studied in 10th standard, that if you take a wire, the magnetic field lines are in circular loops, the intensity decreases as you go away, and the tangent gives the direction of the field. All these pointers are mentioned over here about the Orsted's experiment. So it's not very important, but yeah, you can go through it. You don't have to like waste a lot of time over there, including this one. Just go through it. That's it. Okay, I'm not putting a star mark there. Cool. Now all this is fine. Okay, now these are two examples. Okay, this one and this one. This is application of Ampere's law. This is the first one which you should know. So I will put a star mark. This can come in case study. Let me tell you, case study type of question. And this is basically your second question. Okay, this is your second question for case study. Very, very important. So please do this. Two problems. So case study material, I'm marking it. The graphs also included. Now for solenoid and toroid. Now you should obviously know how the field diagrams look like. What is a solenoid? Solenoid is nothing but a coil. You just take a coil and you wind the current like this. You will see when the current flows, it will produce magnetic field around it. So there will be magnetic field which will be produced around it. The field outside is negligible. Remember that. The field inside is roughly constant. It's not exactly constant. You can see the divergence over here. The field lines will obviously spread, but roughly it is constant inside. Outside it is negligible. Remember these pointers what I am mentioning over here. Great. Next, go down little bit. You will see the application of Ampere's loop law, and you will see the formula mu naught Ni. N is the number of turns, so it must be somewhere on the top. Okay, then the total, yes, it's mentioned here. If N is the number of turns per unit length, very, very important, per unit length. It's not total turns, it's per unit length. So that's something which you should keep in mind. Go down. Toroid. What is a toroid? You take a solenoid and cover it. You complete the loop. It's a solenoid which does not have open ends. So you bend the solenoid so the ends are attached. That becomes a toroid. So inside a toroid, again similar things are valid, like only here B inside is roughly a constant, but if you are here or if you are here, then B outside is 0. Okay, it's not there, it's not present. Keep this in mind. Okay, and you will also see the formula for toroid is exactly same. Those of you are wondering, sir, it looks little different. Let me tell you, it is mu naught. N by 2 pi r is nothing but small n into I. How? Because this is turns per unit length. So total turns by the total length. The total length is the circumference. The circumference of that toroid is 2 pi r. Is that making sense to all of you? Yes, MS Smiley, we are coming to questions also, but these are very important. You should know what to do and what not to do. Okay, this is fine. Go down. Force between two wires. Yep. So force between two current carrying wires. Very, very important formula. Please remember this. Same current will not repel, it will attract. It will attract. Keep this in mind. And opposite currents will repel. This is what the gist over here. Okay, cool. I've put it right over here. This is fine. And this is an experiment. You can just probably study it. Not so important, but yes, can come in case study type of thing. Okay, cool. Go ahead. Nothing else over here. Yes, torque. So if you take a loop which carries current, there will be a torque on it. What is the torque? The torque is going to be here. Yeah. This is magnetic dipole moment. Magnetic dipole moment's definition. The torque is exactly similar to electric dipole moment, M cross B. There it was P cross E, very, very similar. You can see the resemblance right over here. And yeah, if you want, like over here, if the number of turns are there, too many in number, if it's not just one loop, if it is 3-4 loops, you just multiply it by n. That's what you will see over here. If there are many turns, if there are n turns, then this formula is still true, just that you multiply it with the factor of n. That's all, that's fine. Okay, this is fine, this is fine. Okay, circular loop as a magnetic dipole, you don't have to worry about a derivation. Okay, the whole paragraph, I'll tell you in one line. See, it just means that if you have a loop which carries current, and if you have a magnet like North Pole and South Pole, they both behave in a very similar fashion, because this loop produces a magnetic field something like this. This bar magnet also produces field very similar to it. The field lines look very similar, so this is very much equivalent to a bar magnet. So that's what this entire paragraph is all about. So that's something for derivation, but as such you need not know it for objective kind of exam, just know the gist of it. This is important. Current due to a current due to a charged particle which is rotating. So this is the basic of it. If you remember this, you get everything else. Just keep this in mind. Okay, all this is not so important, forget it, but here there is one very important formula, this one, this is important. So magnetic moment upon angular momentum. Angular momentum and magnetic moment are related by this, charge by 2 times of mass, keep this in mind. Go ahead, all this is not important. Moving coil galvanometer, yes, you need to remember. And this is the most important formula. Phi is equal to NBA by K into current. What is this phi? Phi is basically the deflection. What is N? Turns. A, area. B, field. K, torsional constant. Where is K? I will probably see where it is. Where is that K? Where is the definition of K? Just mark it somewhere. Yes, there is the definition right over here. The spring provides a counter torque K theta which balances the torque of the magnetic field, and in the equilibrium condition this is what it is. Now the way to remember this is basically, I had told you, the deflection is basically basketball, and you have a captain over here and the captain, and there is current right over here. That's what the trick is to remember it. How? Deflection is theta or phi. Basketball means NBA, correct? NBA. And captain, K, C, whatever you want to put it, torsional constant, and you have the current. So if you remember it like this, it becomes easier. Is that making sense? Okay, so very easy way to remember this formula. Okay, this diagram, yes, you need to know it, obviously, how galvanometer works. And then, fair enough. Yeah, so galvanometer as ammeter and galvanometer as voltmeter. These two things you need to know. This is one thing, and galvanometer as ammeter. Both the conversions, you need to know that. And what happens? Where do you put a shunt resistance? Is the resistance of ammeter more, voltmeter more? Is it connected in series? Is it connected in parallel? So that thing you need to study. You cannot ignore that. Okay, that's all. Yes, and the summary part, of course, summary you need to go through. Obviously, the points to ponder as well. Let's do some questions. You will get some fun after this. Okay, so this is what is important. I'll just save this. Perfect. Ready for some questions, my warriors? Let's go to some questions. Okay, let's go to some questions. Perfect. There we go. Here's the first question coming up on your screen. The magnetic field interacts with a moving charge only. The moving charge produces magnetic field. What do you suggest? Is this correct? Supriya saying Kirchhoff's law is hard. Yes, it is hard in J, but I feel in CBSE the kind of applications you will get will not be so tough. Spiral and helical. Okay, so Kushal, I'll tell you what's the difference between them. This is spiral. Okay, this is spiral. Helical is when it is like this. This is in 3D. Visualize this in 3D spring basically. That is basically helical. I hope now it makes sense. So that's the difference between them. Okay, many of you are saying A, some of you are saying B. Let's figure this out. The correct answer is actually A. See, I just told you the force acting on a moving charge is Q V cross B. If V is 0, force is 0. We just saw this. If V is not 0, then force is also not 0. So this clearly tells A option is correct or assertion is correct. Moving charge produces magnetic field. Yes. If you take a wire which carries current, what does it have? Electrons, right? And what are these electrons doing? They are moving. So they are moving charges. And what do moving charges do? They create magnetic field around it. They will create magnetic field around it. And once a charge moves, it behaves like a magnet. That's why magnetic fields will apply force on moving charges only. Hence option A is correct. Got it? Not B. Moving charges behave like a magnet, and obviously magnetic field will affect not mass, not charge. It will affect magnets. So magnetic field will apply forces on magnets, and moving charge are nothing but magnets. Got it. Let's move ahead. Energy of a charged particle moving in uniform magnetic field remains constant. Work done by magnetic field on the charge is 0. What do you suggest? Is it A, B, C, D? Easy one. Moving on. But you know, these small things also in exam, I know you guys get confused. You guys make some mistakes. A, B, make it unique saying D. I think D is not correct. Yes, both assertion and reason are correct. Energy of a charged particle remains constant. Reason, the force is always perpendicular to velocity. Work done by that force is 0 since theta is 90. If work is 0, then the kinetic energy will always remain constant. That's work kinetic energy theorem. So that's why this assertion is correct. Work done is 0. Yes, I just saw that. That is work kinetic energy theorem. The reason is also correct. It explains it by work kinetic energy. Work kinetic energy theorem. That's what it explains. So option A is correct. Everything is following. This is directly explaining it. Next question. Very good, very good, very good Arpita, very good Tharun, very good Harry. Let's move ahead. Brajesh, very good Selvendran, very good Kanishk, very good Ritesh, excellent. Let's go ahead. So solenoid question. Solenoid tends to expand when current passes through it. Two wires which are parallel, they repel each other. What about this? Many of you are wrong. D is correct. Yes, both are false. I just told you this. If currents are in the parallel direction, then what happens? Same will not repel. In fact, they will attract. And in a solenoid, currents are parallel to each other, so they will attract. If they will attract, why will it expand? This is wrong, and this is also wrong. It will not repel. Hence D, correct. It's wrong. Next, voltmeter is connected in parallel with the circuit. Resistance of the voltmeter is very large and blocks the current. What do you suggest? Okay, I'm going to talk a little bit less because now I'm started feeling the pain in my throat. Okay. So, I hope you don't mind. I might not come up in that full energy, but I need to preserve my energy, conserve, law of conservation of energy. I need to conserve it for the remaining part of the session. Alright? Okay, so what do you say? Most of you are saying A. Okay, yes, A is correct. A is correct, it's not B. So, voltmeter is connected in parallel with the circuit. That's very true. If you have some device and you want to measure voltage across it, what you do? You connect voltmeter in parallel. Reason is the resistance is very high. Because it is very high, whatever current comes over here, it directly goes in the device. Hardly negligible current will flow through this because it has very high resistance. So all the current flows here and it's very large and it blocks the current. This is correct, and this is the correct reason for that. Perfect. Alright, moving ahead to the next question coming up on your screen. Magnetic field lines can be entirely confined within the core of the toroid, but not within a straight solenoid. The magnetic field inside a solenoid is uniform. What about this? Very interesting. Many students are going to make a silly mistake right over here. So you have a solenoid, and then you have a toroid. This is our toroid. So this is toroid, this is solenoid. Answer the question. Many of you are saying B. A lot of you are saying going for B, more towards B. Very few people are saying A. See, understand the difference is that, oh by the way, let me tell you the answer is C. Okay, many of you went wrong. In a solenoid, I told you, right? Many of you are going to be wrong in this question. In a solenoid, who said the field is uniform? The field is approximately uniform. B is approximately constant. You can see the end, it is weak. At the center, it is strong. So obviously, you can see that the field inside the solenoid is not uniform. Field lines is entirely inside within the core of a toroid, but not for a straight solenoid. Yes, you can see that the field lines are there outside little bit over here, and inside though it is also there, outside also it is there, but when you go very far it becomes zero. For a toroid, there is no way to escape. For a toroid, understand, there is nothing like to escape. The field lines are just trapped here. So B out is just going to be 0. Yep. Yes. So very important. Assertion is true. Yes, the field lines are entirely within the core. What is the core? This is the core. It is within the core of the toroid. But for a straight solenoid, it's not. It comes out, goes like that and comes back. Goes out, comes in. So the field lines are inside for a toroid, but it is not for a solenoid. Correct. Got it? Yes. Field line inside solenoid is uniform. Wrong. See, for an infinitely long solenoid, for a very infinitely long solenoid, the field is constant. For a finite solenoid, it is not constant. Suhani got it? Akib got it? Yes, for a very large solenoid, very large, 2 meters in length, core is hardly 1 centimeter. Yes, you can take it. So that's the concept. So for toroid, the field is trapped in the core. For solenoid, it is not trapped because it can go out and come back. So that's why it's said that the field is not confined within the solenoid. For toroid, it is. For solenoid, the field is not uniform, it is non-uniform technically. Only for long solenoid, it is uniform. Got it? Very good. Next, passage, you know what to do. Take a screenshot. Once you have taken the screenshot, please put up a heart so that I know you have taken a screenshot. Please do that right now. Put up a heart once you have taken the screenshot, my warriors. Yep, please do that. Okay, looks like I have not even studied so much for my exam. I'm studying so much and working for you guys a lot. Yep. Okay, I wish I would have studied even just like how I'm teaching. I would have studied this much, then I'm pretty sure I would have scored very good marks, even better than what I have scored during my times. Yeah. So please don't let me disappointed, please don't disappoint me by your scores. Make sure that you are going to work very hard, okay? Because I'm doing so much for you. All right, so let's do the questions coming up on your screen. The speed, yep. Yeah, this PDF will be uploaded on the Telegram group, definitely. The speed of the electron is now doubled to 2v naught. The radius of the circle will be changed to how much? Question is that. My score was something around, in board examinations it was, I think, something like 85-86%. Yeah, overall, but in PCM it was more than 90%. So the score which matters was more than 90%. Yeah. So if I was studied like this, I would have scored for sure 95 plus. All right, chalo. Let's see. B, C, B, C, B, C. Answer is B, not C. Why is it C? Yeah, R is mV by QB. So V is doubled. R will also double. So that's why 2 are not. Simple? Yep. Yes, Nidhi, we'll come to case study on transformer also after this. Let that chapter come. Okay? Just hold on, Nidhi. Very good. Thank you, Arpita. All right. Now, Surya, how come you have physics exam tomorrow? It's there, after 2-3 days. All right. Next, if the speed is doubled, then the time required for a revolution will change to how much? Come on. This one is easy. Selva saying C, Harsha saying B. Interesting. Akash saying C, Suhani saying B, Aman saying C. Come on, think. Well. Many of you are wrong. Some of you are correct. The answer is C. Think the time period actually is 2 pi m, okay, by QB. That is the answer. In fact, if you shift it little bit, if you take 2 pi by t, it will become QB by m is 2 pi by t, which is omega, which was a formula I gave you some time back. So it is not dependent on velocity. So no matter what you do with velocity, time period will remain the same. That's it. As simple as that. Yeah, very good. Moving ahead. Next, a charged particle is projected in the field with this much magnitude. The acceleration of the particle is found to be this much. What is the value of x? What is the value of x? Come on, let's do this. What is the value of x? Come on, my warriors, figure this out. Field is given, acceleration is given, find the value of x. Many students will find this question little difficult, but if you think carefully, if you have been paying attention, you will get it. So Surya, if you have not covered EMI and AC, then I would suggest you to just cover EMI, Faraday's law and Lenz's law at least from my lecture. There is one lecture in Pathfinder for Faraday and Lenz's law. Just watch it, solve the questions and read through NCERT and attend my class today. What is important, what is not important. That's it. Do that. That much is enough. Okay. Thank you, chess and football. Okay, let's do this. Well, I'll tell you what. To solve this question, remember force is Q V cross B, and force is also mass into acceleration, correct? Now, here is what I want you to understand. The force is always perpendicular to the velocity. It is also perpendicular to the magnetic field, correct? Because V cross B, right? So force will be perpendicular to velocity and magnetic field both. But force is parallel to acceleration. So from these two, isn't acceleration perpendicular to field? Acceleration is perpendicular to field, and when two things are perpendicular, what happens? Their dot product is 0. So A vector dot B vector will be 0. That's it. Use that concept and solve the question. So acceleration, that means xi cap plus 2j cap dot 2i plus j. That multiplication does not matter because it is anyway 0. So A dot B is 0. So x into 2 plus 2 into 1 is equal to 0. I think there was something missing over here because it is not going to match anywhere. This is going to come out to be -1. None of them are matching. I think this over here, if I remember it correctly, when I was solving in the morning, I think there was a 4 somewhere. I think there was a 4 somewhere. I think that 4 is missing over here. So if that 4 comes over here, this becomes 4 and this will become -4. And then, oh my god, look at this symbol. This is also wrong. This is supposed to be second square everywhere. Looks like we have a printing mistake right over here. Okay, so ignore that printing mistake. That 4 was there, my warriors. I'm so sorry. Okay, so I think, yes, you will see the answer should be -4. Yep, this was 4 over here. But did you understand the concept? Dot product. Why dot product? Vectors are perpendicular. Which two? Force and velocity. Force and magnetic field. Remember that. That will be helpful. How is force parallel to acceleration? Very simple. Suhani, I'll tell you. Force is mass into acceleration. So force and acceleration are parallel. So if you apply the force here, acceleration will be in the direction of force. That's why. Got it? Cool. Chalo. Moving on. Electron has velocity not perpendicular to B. Then the trajectory is, yeah, simple. Come on, do this. Come on, do this. So Lata, in the previous question, I just repeated. Force is parallel to acceleration, but force is also perpendicular to field. So acceleration is perpendicular to field. That means the dot product is 0. That's all I have done. Very good, my warriors. Option C is correct. So remember one thing. If the velocity is perpendicular to the magnetic field, then the path taken is circular. It is a circular path, that is the radius. But if the velocity makes an angle, then there are 2 components like I have been telling you even before. And where is it? The field is over here. So one part will try to make it go in a circular path, but it is also going to move forward. So you will see a path something like this. A path something like this. This is called as a helical path. Okay, so this is called as a helical path. Keep this in mind. This distance between them is called as the pitch of the helix. That's what it is. Okay, moving ahead. If the charge is moving parallel to the field with constant velocity, the force acting on the electron is, come on, please do this. Okay, why can't it be a straight line? It can't be straight line because it's being propelled at an angle. It is thrown which is not parallel to the field. So whenever you throw it at an angle to the field, it has to get some force. It has to experience some force, so it will deflect. So it can't be a straight line. Thank you, Afrin. Okay, many of you are saying A. Okay, so I know what you guys have done. So the force acting is charge into V cross B. Guys, you forgot this cross is nothing but sine theta. This theta is nothing but 0. So this force is also 0. Read it. Parallel. Parallel means theta is 0. So the answer is D, not A. Be careful. This is how you are going to lose marks in the exam. Be careful. Let's go to magnetism and matter quickly. This is a short chapter. This is a short chapter. Open up your NCRTs quickly. Let's go to the NCRT. We are going to see what are the important points moving in the NCRT. Open up your NCRTs, my warriors. We are going to solve some questions, but before that, important points. This chapter has many things deleted, so you should be happy about it. If you are happy and you know it, just put a smiley in the chat box. Okay, so these are some not so important, but yes, you can go through this particular paragraph. Okay, just read it once. Just go through this paragraph. Okay, it's not so important, but yeah, you should know it. Go down. Okay, and okay, this is fine. This is fine. The tangent gives the direction of the field. Yes, these are the properties of field lines. The field lines are closed loops. Very, very, very important. Tangent gives the direction of the field. Okay, that is standard. But just unlike electric charges, where the field starts from a point and ends at a point. This is electric field. But for a magnet, it does not happen like that. It is a continuous loop. So for magnetism, it's a complete loop. Keep this in mind. Fair enough. Go down. Okay, now this is again a repetition, large number of field lines, stronger magnitude. So the strength of the field is directly proportional to the density of lines. That's standard. They do not intersect. That's also important, which you have seen again before. Okay, this and all is fine. Just go down below. Okay, now see, this is also again a little bit of repetition. If you remember, I just told you a loop. I just told you just some time back, a coil is like a bar magnet. A coil is like a bar magnet. So if you have a solenoid, which is nothing but coils, this is nothing but equal to magnets placed one before the other, like this. So what will it behave? This will behave like a big magnet. That's what this entire paragraph is. One coil, okay, one coil, see this guys, one coil is a magnet, solenoid is coils, so many magnets, so it will become like a big magnet. That's what this entire jhamela is. They have unnecessarily tried and confused you. Okay, so ignore. So all this derivation is not there. By the way, dipole in uniform magnetic field is deleted. It's not there in the syllabus for you guys, so you should be very happy about it. Go down, go down, go down, go down. Okay, electrostatic analog not there, don't worry. Okay, go down. Magnetism and Gauss law, well, they have not explicitly mentioned it, but yes, you can remember this particular thing. What it means is that net flux for magnetism is always zero. It makes sense because magnetic field lines are always closed loops. Magnetic field lines are always closed loops. So if somebody decides to choose some closed surface like this, if this is a surface, closed surface, whatever field lines are going in, same field lines are coming out. So whatever is going in, if it is negative, the field lines which are coming out are positive, net flux will be zero. That's what it says. This is equivalent. Net flux is always zero. Got it? Thank you, Cyberpiece. Keep this in mind. Go down. Yeah, so this is what is mentioned right over here. This is net flux through a closed surface is always zero. Very, very important. And this also, that the magnetic element is a dipole. All magnetic phenomena can be explained in terms of dipoles. Basically, there are no monopoles. That's what it also says. There are no monopoles. Everything is a dipole. There is no north separate and south separate. You always get magnets as quantities of two pairs, north and south together. Okay. Now over here, what and all you have? Field lines. Okay, that is okay. Go down, go down. These are all problems, so you can go through. Earth's magnetism, yes, you need to know this. So go down. Over here, yes, this diagram is important. This diagram is important. Earth's magnetic field, Earth's magnetic equator, geographic equator, declination and inclination. Yes, you should know this. Then go down. Angle of dip, yes, you should know this diagram. If you want the detailed theory, I have done a class just on Earth's magnetism. It's hardly 1 hour class. If you want it, watch it. It's there. I've explained everything in detail. Okay, that's very, very important. In terms of formula, because it is very easy. Plus, you get questions from these particular topics. So just remember this angle of dip. Okay, and what happens to poles? What happens to compass needles at poles? So important case study. You can remember this. Very, very important. Do this. Go down. This and all is deleted. So be happy. All this is not there. Whatever is there after this, para, dia, ferro, permanent magnets, all this is not there. Ignore, 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 ignore. All this is not there. Retentivity, coercivity, not there. So directly you come to the summary part. Now this summary part, obviously you need to go through and this one, points to pointer. Please go through this as well. I'll just save this. Let's go to some questions. Let's do some questions. Very good. Okay. Look at the poles. Look the poles, sir. Tarun. Look at the poles. Acha, somebody wants, sir, what is the dip and all that. Okay, I'll just explain to you in brief. Okay, I'll just explain this to you in brief. Let me bring the earth. See guys, see, this is the earth's axis. Earth's axis, let's say I've kept it like this, vertical, and this is the equatorial plane. Okay, everybody getting this? This is the equatorial plane. This is the earth's geographical axis. Fair enough? Now, the problem is the earth's magnetic axis is not vertical, or it is not the same as the geographical axis, the axis about which earth spins. The problem is the earth's magnetic axis is at an angle, and what happens is, you can see this is Canada, this is America. I don't know whether you can see it so clearly, but yes. Okay, so what happens is the earth's magnetic poles are here somewhere in Canada and down here in Antarctica somewhere here. So the earth's magnetic axis is slightly tilted. So earth behaves like a bar magnet which is slightly tilted in nature. The axis is tilted. So the equator will also be tilted for the earth's magnetic properties. For geographical properties, this is one half, this is other half. But a sphere can be divided into two halves like this also. You cut it like that. So if you draw a magnetic equator, this is magnetic axis. Fair enough? Okay. So the field lines go like that, come over here at the North Pole, and they go start from here, the South Pole. Okay, so they go like this. So these are the magnetic field lines. Now this difference is not so much, it's negligible. Okay, but in reality, remember, they are actually little bit apart. They are few kilometers apart for sure, in fact few thousand kilometers apart. But on Earth, on this globe, it looks very small because the Earth's radius is 6,400 kilometers. Anyways, coming back, the field lines, when they go like this, understand, when they brush past the Earth, over here, they are parallel to the equator, roughly. If you notice, the field lines go like that, the field lines go like this. So if this is the Earth, let me just put it over here. Okay, so the field lines which are there, okay, so they go like this, like this, like this, like this. Can you see they are almost parallel at the equator? Almost parallel at the equator. So if there is a person standing here, okay, if there is a person standing here, it will be horizontal for him. Does it make sense? But if there is a person standing at the pole, there is a person standing at the pole, then it will be vertical. You can see that the field lines are vertical. But imagine there is another person who is standing somewhere else. Then the field is at an angle. Can you see the field is at an angle? So if this is the horizontal, okay, imagine this is the ground surface. This is the person standing over there. Then the field might make some angle with the horizontal. So it will have two components. One is the horizontal, one is the vertical. This angle is called as the angle of dip. When you draw the triangle, this is called as the dip angle. It can be positive or it can be negative. Is that clear now? Okay. Is that understood, everyone? That's all this is. This is the dip angle. Perfecto. Moving on to some questions. Assertion reason, planar circular loop of area A and carrying current I is equivalent to magnetic dipole of dipole moment M is equal to I. At large distance, the magnetic field of that loop and the magnetic dipole is same. So what do you guys think? As SJ Priyadarshini, I have arranged for the PDFs. As soon as this session is over, you are going to get it. Don't worry. Okay, SJ? Okay. Let's go ahead. Earth's magnetic formula. You can assume Earth to be a magnet and apply all the other formulas which you know for a bar magnet. Okay, that's all. Cool. We don't have magnetic intensity. We don't have magnetic susceptibility. All this is not there. It's deleted from the syllabus. Don't study unnecessary things for CBSE perspective. Okay. Well, many of you are saying C. The correct answer is A. How? There is a loop of area A which carries current I, it's equal to a magnetic dipole of moment IA, which is correct. So if you have current I and the area is A, the magnetic moment is number of turns into current into area. This N is equal to 1 because it's just one loop. So N is equal to 1. So this is correct. At large distance, the field of a circular loop and magnetic dipole is also the same. That's correct. If you take a bar magnet or even if you take a coil which carries some current, you will see that the field lines roughly behave the same way for a loop as well as for a bar magnet. And that's the reason why you are calling this as equivalent. You are calling this as equivalent to magnetic dipole moment of the value this much. So yes, the reason is correct, and it also explains because the field lines resemble. The field lines are very, very similar, the field lines. That's why you can convert a loop into a bar magnet. Is that understood? It is not C. Both are correct. Some of you said C. Some of you thought the reason was wrong. The statement is correct, guys. The field lines resemble. Is that okay? Cool? Everyone? Fair enough? Got it? Shall we go ahead? All right. Moving to the next question. Here we have, when the radius of a loop which carries current is doubled, the magnetic moment becomes 4 times. When magnetic moment depends on the area of the loop. Well, is this magnetic moment depends on the area of the loop correct? And is it the correct reason for the this particular assertion? Come on. Think. Uncharted saying A, Ashika saying A, Rishabh confused, Akib saying A, Vignesh also A, Mukesh also A. Very good, you guys are correct. Finally, when the radius of the loop is doubled, then the magnetic moment, which is NIA, but remember area is pi r square, so r square will become 4 times because r has become 2 times, so 2 square is 4, so the magnetic moment will also become 4 times. Oops. Now, yeah, this is correct. Yeah, fine, this is correct. So when the current is doubled, then the magnetic moment becomes 4 times. Magnetic moment depends on the area of the loop. Yep, you can clearly see it depends on the area of the loop. So it is correct. Perfect. Moving ahead to the next question. Domino, you don't have to remember dimensions. You just have to remember formulas. If you remember formulas, each quantity's dimensions you remember, from that you can derive dimensions. No human will remember dimensions, okay? Nobody who even tops board will remember dimensions. Earth's field does not affect the working of a moving coil galvanometer. Earth's field is too weak. Is this reason the correct reason or is it false? Come on, what do you guys say? A, D. So when you use a galvanometer, do you worry about the earth? I'm pretty sure we don't worry about the earth because the magnet inside a galvanometer, so the magnet inside the magnetic galvanometer has a field, okay? So the magnet inside the galvanometer has a field of the order of 10 to the power minus 1 or 10 to the power minus 2 Teslas. But the magnetic field of the earth is of the order of 10 to the power minus 4 Tesla. You can clearly see this is much smaller than this. So it is very weak and hence it explains it properly. Hence option A is correct. No, it is not D, it is not C, it is option A, my warriors. Be careful. Moving ahead to the next question. A compass needle when placed at the pole rotates in vertical plane. The earth has only horizontal component of the field at the poles. Very interesting question. Let's see if you can get this. Come on, my warriors, figure this out. Paper will be easy, Varsha. Well, I don't know. Paper can be hard also. But we are going to prepare for easy and hard both. We are going to solve hard questions also. Okay, tomorrow questions will be much tougher. Day after tomorrow it will be even tougher. So we're going to do all kinds of things. If it is not hard, good for you. Then you know how to solve it. Alright, C and D. A lot of students confused between C and D. Well, actually C is wrong, D is correct. First of all, let me tell you, for the earth at the pole, okay, the magnetic field lines are in fact vertical. It is vertical. So basically BH is 0. BV is not a 0. The earth has only horizontal component? Wrong. In fact, it has vertical component, horizontal is not there. The needle, when placed at the pole, rotates in vertical plane? How is it possible? When you place a needle over here, then the needle itself will become like this. It will point downwards because the magnetic field is down. So remember, whenever you take a needle, right, the needle always points in the direction of the magnetic field. So this is how the needle behaves. So the field is down, so the needle will come down. It will not rotate. Why will it rotate in the vertical plane? Doesn't make sense. Be careful. It will just point. It should have been mentioned. It points downwards. Okay, here we have a question based on, you know, the Earth's magnetic field, the planes. Now, geographic meridian, magnetic meridian, these are the planes. You have to take a picture of this. But let me quickly explain this to you. Remember, I had just told you that if this is the horizontal, the Earth's magnetic field, I just told you, Earth's magnetic field will have two components. One is vertical, one is horizontal, and this angle is often called as the angle of dip. I've just told you this, and all of this happens in a plane called as magnetic meridian. Remember, if you keep going in this direction, you won't get the Earth's pole. If you keep traveling in that direction, you won't get the Earth's pole. You will get the magnetic pole. So it points towards the magnetic pole. The actual Earth's pole, remember, magnetic axis is different from Earth's axis. The actual Earth's pole is slightly different, so it is at an angle. So if you go in this direction, you will get the geographic pole. So that plane which is at an angle, that is your declination angle. You can call it phi, you can call it delta, whatever you want to call it. Okay, so that is your declination angle. That's what this whole passage tells you about. Okay, please take a picture of this and post a heart once you are done. Post a heart once you are done. Then we'll start solving the questions. Very good, very good. Let's move. Come on, let's do this. Come on, guys. You two at least are sitting at home. I am standing here just for you. I am more tired than you. Come on, but I'm not going to give up. Let's do the first question. Thank you so much, Rishabh, Kritika. Very good. Hemant, Akash. Let's get going. Sneha, Ganesh, Akib, Cyber, Naveen. Very good. Here we have the first question. In a certain place, the horizontal component is 1 by root 3 times the vertical component. The angle of the dip at that place is pi by 3, 0, pi by 2, pi by 6. Come on. So Mr. Abid, you can do one thing. There is a Pathfinder lecture. Just search Shreyas sir, Earth's magnetism. You will get that lecture. Just watch that lecture in detail. You will get it. Okay, Mr. Abid, do that. Okay, B. Sure. Perfect. Very good. Proud of you, my warriors. Or just replay, na, Mr. Abid. Just replay this session. You will get it. So that's it. This is vertical. This is horizontal. This is angle of dip. Khatam. Do it. It's clearly mentioned. What is it? Tan theta, if it is vertical by horizontal. Horizontal is 1 by root 3 times of vertical. VV goes. So it will become root 3. So if tan theta is root 3, so theta is 60 degrees. Done. Perfect. Moving ahead to the next question. The angle between geographic north and the north shown by the needle, actual geographic and the north which is shown by the needle, is called inclination, declination, meridian, magnetic pole. This is very interesting. Thank you, Dheeraj. Thank you for that fire. Okay. Probably now that will burn some more calories for me. Very good. Let's see if you guys are getting it. Very good. Magnetic declination, that's the correct answer. Like I told you, if the needle points in certain direction, then if you go there, you will get the magnetic pole. but actual Earth's pole, the geographic pole, is in some direction, some other direction. This is somewhere else. So that angle is called as declination angle. That's option B, correcto. Very good, very good. Moving ahead to the next one. The angle of dip at the pole and the equator respectively are, what is the angle of dip at the pole and equator respectively? Inclination. Inclination is different. Inclination is, see, when you have an inclined plane, that's it. So what is the inclination of the plane? That's with respect to not just magnetism, in general for anything. Inclined plane, inclination of that plane, that is called inclination angle. Okay, don't get confused. All right, moving ahead, D or B? B or D? Many students are confused. Guys, you got confused. The answer is D. Look at it carefully. This is the Earth. This is the Earth's magnetic field. This is the equator. Over here, the magnetic field is making 0 degrees with horizontal. Dip angle is always with horizontal. Over here, the magnetic field is making 90 degrees with horizontal. So pole and equator, 90 and 0. So 90 and 0, that's the answer. Got it? Yes, parallel is 0 degree, perpendicular is 90 degree. Got it? Very good. Moving to the next one. There is a needle which is allowed to move in a horizontal plane. It is taken to a magnetic pole. How will it behave? It will become rigid, it will stay in any position, it will stay in north-south, it will stay in east-west. Very good. Excelente. Muskan saying D, Aman saying A, Iniha Lakshmi saying A, Naveen saying B, Kingsley saying A. कितना न्यूमेरिकल आएगा पेपर में पैटर्न देख लो निखिल. Yeah, there are 45 questions compulsory which you have to give in all. ठीक है, और सारे के सारे न्यूमेरिकल्स ही रहेंगे. Some of them could be, I don't know, some of them could be conceptual like this or theoretical. हो सकता है. But 45 are the total number of MCQs. See, I'll tell you what happens. Many of you are saying D and some of you are saying B. Confused ho gaye. See, if you are at the pole, let's say this is the Earth's pole. Basically, this is horizontal plane. Then, at the pole, the field lines are all vertical. Okay, at the pole, the field lines are all vertical. So, what will happen? Actually speaking, the magnet wants to align down. In horizontal direction, it has no force. So, in horizontal plane, the torque on the magnet is 0. Because the torque is trying to pull it in the vertical direction. But nothing, there is no torque in the horizontal plane. I hope you agree with this. Because of this, no torque, so wherever you keep it, it stays there because there is no torque on it. You keep it like this, it stays there, no torque. Keep it here, no torque. That's the problem. Only when there is a component of magnetic field, let's say Earth's magnetic field is like this, so there is a horizontal component this way, then the magnet will decide, okay, I want to be aligned in this manner. So the needle will align in the Earth's horizontal component direction. When there is no horizontal component, where will it align? Nowhere to align. Hence the correct answer is actually B. Yep. Yeah, you can join the crash course even today, Kaushik. You would have just missed one day, but you'll get the recordings. Even today you can get the recordings. And I think it's better to join as soon as possible, because the later you delay, you'll start procrastinating. You will think like, okay, I'll do then, I'll do now, I'll do later on. But it never happens, and then you start losing out on days, and it's better to finish the portions early than to start later on. Which of the following is correct? Okay, I don't know why this came, but anyways, this was not supposed to be here, but still. Okay, select the correct statement of the following. Dip is 0 at the center, dip decreases as we move away, dip increases as we move away, dip does not vary from place to place. This is directly dependent. This is directly dependent on the last question. Everybody, come on, this is very easy. I just told you. At pole, it is 90. At equator, it is 0. So it depends from place to place. Hence, the dip increases as we move from the equator to the pole. Because we just saw this. No, it is not A. And dip is 0 at the center of the earth. Guys, dip is not even defined at center of the earth. Dip is only for the surface of the earth. Okay, it's not when you go inside the earth. This is not even making sense. So as you go from here, so it goes 0 to 90 degrees. So it becomes more. It increases. Hence this is correct. Perfect. Moving ahead to the next part, but before that, a break. 15-minute break. Which all chapters are we going to do? So let's just write it down over here. Okay. Electrostatics. Electrostatics is done. Gauss law is also done. Current is also done. Capacitors is also done. Magnetic sources also done. Magnetic properties also done. So the only things which are remaining is EMI and AC. Okay, so after the break, that's what we're going to do. Fair enough? Very good. Chalo, let's start the timer. 15-minute timer right over here. How many of you are going to have coffee? Please let me know. How many of you are going to have tea? What are you guys having for break? Yeah, you didn't tell me last break. We directly started off. Thoda freshen up karo, please. Thoda sa. 20-minute break. Buddhi Raja, it will be over very quickly. And plus more other sessions are also there on Enthuse, so that also needs to happen. So that's why not 20-minute break. Okay, kya baat hai? Lunch. Chalo, lunch kar lo. Somebody has to pray. No problem. Pray and have bath. Okay, quickly finish your prayer and have bath. Glad to know that. So let's start this session after 15 minutes. I'm going to see you. Have your coffee, have your bath, have your chit chat, whatever you want to do. Just come back after 15 minutes. Okay, promise. Starting the break now. Hello, welcome aboard. Welcome, my warriors. Welcome back. I hope you are all back into the marathon session with me, Shreyas, your physics master teacher. And welcome to Enthuse, the dedicated English medium channel for all the board preparation and all the engineering entrance preparation like KVPY, JEE, you name it, VITSAT. Yes, welcome aboard. I hope you can all hear me loud and clear. Good evening, good evening. Chalo, on to the last leg, fruitful session. What an amazing session. Those of you are joining in late or those of you are joined midway, let me tell you, you can watch the replay after that. But does not mean you start watching the replay now only. First attend the live class. The experience of live class is completely different and I'm pretty sure all the students out here will agree to that. So let's get going and let us open up the next PDF of electromagnetic induction. So open up your NCERT. Yes, please open up your NCERT. Oh no, I did not have my lunch. I had banana, I had biscuit, and then I had, what else did I have? Yeah, I had some chickies and some hot water. That's all. So I'm going to have lunch after this entire session is over, because if I have lunch, I take some time. I need to have my lunch in peace. So I will not have it in a hurry. So cool. So all this just for you so that you can score well. Okay. So please, please, please don't disappoint me later on. Okay. So this is done. Okay. Wait a minute. Let me just save this once and for all. Remove. This is also saved. Done. This is your next PDF. Let me just open this. Okay. Yes, electromagnetic induction is here. Let me also load alternating current because I'm going to need it next. Okay. Yep. There we go. Very good. Yes, I'm good to have all of this. Perfect. Perfect. Just give me a sec. Done, done. All right. There we go. Okay, chalo. Let's start doing this quickly. In EMI, what and all are the important points that you need to remember? Actually, EMI is very small, I'll tell you, because theory-wise, it's not too much. See, this is the definition of electromagnetic induction. If you are searching for it, that's here. Okay. We will study the phenomena associated. Let me just put it. Okay. The phenomena associated with changing magnetic fields in which the electric current is generated by varying magnetic fields. Varying is appropriately called as electromagnetic induction. That's what the definition of EMI is. It's right over here. Now, the first experiments by Faraday and Henry are at the beginning, where they talk about how turning on, turning off the coils or moving magnets produce electricity. So the two famous experiments and all the experiments related to changing of flux and how it created electricity is there. Now you will have the definition of magnetic flux right over here. This is very much similar to electric flux. Okay, it's very, very similar to electric flux. This has the unit of Weber. So 1 Weber is 1 Tesla into meter square. So that's the unit. Go down. Okay, Faraday's law. Then we go to Faraday's law. And this is what it is. Very, very important. E is equal to minus n d phi by dt. What is n? N is the number of turns. D phi by dt is nothing but rate of change of flux. That's what it is, a rate of change of flux. Fair enough. Okay, so that is the rate of change of flux. Moving ahead, let me just put it over here maybe. Okay, good. Go down a little bit. Now you will also see the reason why that minus sign is there. These examples are pretty much straightforward. You should do this. That's where you come across Lenz's law. The polarity of induced EMF is such that it tends to produce current which opposes the change in magnetic flux produced by it. That's the significance of that negative sign in that particular equation. It says whatever direction the flux try to change or increases, it will always try to oppose it. That's how the current is induced inside any coil. Okay, so this is fine. This and all are examples. If you are confused with the direction, then please go with it. If you are confused with the directions, then please go through this. Okay, that's the paragraph that you should read. Okay, then go down over here. This and all are examples. Okay, motional EMF, I didn't see that in your syllabus, so ignore. Okay, but still, if you want to know it, it's BLV, that's the standard formula. It can come as case study. I'm not denying it cannot come as case study, it can come as case study. So still I would say remember this formula for motional EMF. So whenever you move a rod of certain length in a magnetic field, then there is EMF produced across it, which is BLV. Okay, keep this in mind, that's all. Now otherwise it is there in JE syllabus, we'll do that during JE, don't worry about it now. Okay, all this energy consideration, a quantitative study, it's not there, ignore. Go down, all this is not there. Yeah, eddy currents is there. So please read this paragraphs. Okay, so please read this paragraph, and they have explained it right from here in this example, this diagram they have taken. See, what is eddy current? Let's say this is a metal object. You move it in a magnetic field because the flux through it changes. The flux changes. What does flux change create? Electricity. What does electricity mean? Current. What does current do? Current will create energy loss. How? I squared R. That means there will be heat loss, I squared R loss. So if you move this metallic object in magnetic field, there will be heat loss. Where will this energy come from? Because I am doing work. So there is loss in mechanical energy, which is lost as heat. Those currents which are there, they are in random shape, they are in loops. That is why it is called as eddy current. That's all it is. Thank you, Avanti, so much. Go down, remember all this. Okay, so they have explained few phenomena, so go through this. So please go through 1, 2. I'm not putting a star mark. It's not about being important, it's just that you should know the applications of it. Okay, damping, induction furnace, electric power meters, all these are important applications. So please go through these 4 applications right over here. Okay, then you have inductance right over here, and wait a minute. Yeah, so let me just mark it. So the flux, oops, one sec. Okay, so what you can do to remember all this is the flux is self-inductance into current, and d phi by dt with negative sign is minus L di by dt. d phi by dt is nothing but EMF. That's what this is. Rate of change of flux is d phi by dt is L di by dt. Keep this in mind. And the flux which is linked is equal to n phi b, and that is proportional to the current. That's what it has been mentioned over here. So basically the concept out here is, I'll tell you, let me put it over here. See, if you have a coil which carries some current, then there will be some magnetic field which will be passing through the coil just because of that current. That flux, if it is calculated, through that area, that flux is over here, that current which is rightly mentioned over here is here. So how much flux is produced by that current? That proportionality constant is called as self-inductance. What is it called? It is called self-inductance. That's what this is all about. Now there is something called as mutual inductance. So mutual inductance is when the current in one causes changes in the other or induces electricity in the other. I'll give you a simple example. Imagine you have a coil which carries current. Let's say I call this as the primary coil. Now this primary coil will produce magnetic field, obviously, and some of these field lines may pass through another coil. This I will call it secondary. This is the secondary coil, and therefore there will be some flux associated over here. That flux is mutual inductance into current in the primary. This is the mutual inductance coefficient. That's something which you should remember. Number two, okay, you should also know that this M does not matter whether you make this primary, this secondary, or this primary, thus secondary. So that is what, you know, M12 or M21 doesn't matter which one is primary, which one is secondary, it's all the same thing. Now the next thing that you should remember right over here is, going down, the formula for mutual inductance when you have two solenoids which are coaxial, concentric solenoids. This is a very, very important formula. What is N1, N2? They are the turns per unit length for each solenoid. N1, N2 are turns per unit length for each solenoid. This small l is the length. Okay, if you are wondering what that small l is, that is nothing but the length of the solenoid. Where is it? Okay. Where is it? Okay, here everything has been mentioned. So the number of turns per unit length of solenoid 1 is N1. The corresponding quantities for outer solenoid is N2, R2 and all of that. Capital N is used for total turns, that's another thing. Okay, small l is the length of the solenoid. If it is not mentioned, let me put it over here. Small l, let me go over here. The small l is basically the length of the solenoid. Keep this in mind. Very, very important. All right, go down. Everybody clear till this point? Yep. Do we have AC generator? Yes, you have it. Okay. Now, this is something which I told you before also. M12 is M21. Basically, what you make primary or what you make secondary doesn't matter. It is going to be the same coefficient. That's what it is. Okay. So, this is very, very important. So, this equality is very useful. That's what is mentioned right over here. Okay. Moving ahead. Okay. These are all problems. Okay. Now, what is this? Like I just told you, flux is M into current in the primary. So, minus d phi by dt will be minus M dip by dt. What is d phi by dt? This is nothing but EMF. That's what has been done over here. EMF is minus M di by dt. That's it. EMF is minus M di by dt. That's something which you should remember. It's the same thing. If you want to remember it this way or this way, really doesn't matter. You should know how to apply the formulas. Okay, all these things I just gave it to you in the previous slides. So, you know, the flow of events, the flow of chapters, the flow of topics is not so great in this chapter. So, I have already discussed this before. So, please refer to the formulas before. Already done. Refer before. Okay, so it's already done. All these things. Moving ahead. Okay, just remove this. Cool. Go down. Self-inductance of a solenoid, that's something which you should remember. This is for a solenoid. What is small n? Turns per unit length. What is small l? It is the length of the solenoid. Standard definitions. Okay. Now, energy stored in a solenoid, this is half Li square, something which you should know. Half Li square, keep this in mind. And all this, see guys, there are a lot of things NCERT will try to confuse you. Please ignore. Remember only the things which I am telling you. Other things are not at all necessary. AC generator, you should know. You should know the working behind it, how it works. Now, the idea behind the AC generator is, there is magnetic field, there is a coil, area vector A, it rotates with omega, that's it. As soon as it rotates, this theta will change. So remember, flux is BA cos theta. If theta changes, flux changes. If flux changes, it will create EMF. That's the basic fundamental of a generator. The area rotates, theta changes, flux changes, flux change, Faraday's law, electricity. That's the basic rule of finding or understanding what a generator does. Now everything has been explained here, but the main formula is right over here. Okay. Now instead of remembering this formula, I would ask you to remember the formula in this way. The EMF is Born, remember the word born sine or cos omega t. So this is a much better formula to remember. Born sine omega t. Isn't it easier rather than NBA, this omega? Nah, not so great. Yep. AC generator is not deleted. What makes it rotate? The turbine is attached to this generator. The turbine is rotated by the water falling on it, or some steam engine or the diesel engine, something will rotate it. Some external force, some external power will be used to rotate the generator. That's how it works. Is that clear, Mr. Abid? All right, let's go ahead. Omega is the frequency and all of that. Okay, this is just the graph of it. This and all is fine. Okay, so there we come to the summary. So please go ahead with the summary, read it properly, don't skip pointers unless something is deleted, and also the points to ponder. Do not skip this. Like I've been telling you, these things are not so important. Ignore that. You can remember the dimensions very easily. Let's go with our questions now. So I'm just going to save this so that I can share this with you later on. Perfect. So going ahead with our questions. Okay, there we go. Get ready, guys. I hope you are ready with your rough sheets and pens and your brains out. And yes, I'm going to have a formula revision with application. So that's tomorrow at 11 o'clock. Everybody remembers it. Please make a note, set your alarms 11 o'clock. Shreyas sir is going to be live, but it's not going to be as long as this session. It's going to be much shorter, but there will be a lot of problems where you learn how to use the formulas. That's what it's all about. Here's the first question. There we go. So Praveen, make sure you join the Telegram channel. So guys, if you're asking how to get the PDFs, join our Telegram channel. The link is there in the description box below. Please go ahead. Okay. Acha, if AC generator is deleted, don't worry, Anishka. Think of it like a case study. Okay. So that's it. But as far as I remember, it was not deleted, but it's okay. Just think of it like a case study question. Solve this question. Come on, my warriors. What is the answer? A. Okay, B, A. B it is, it's not A. The number of turns of a coil is increased, it becomes difficult to push the bar magnet towards the coil. Makes sense. If you have more turns, then what happens is the flux will increase. So if you take a bar magnet and you push it towards that coil, it becomes difficult because by Lenz's law, and basically Faraday's law, what will happen? The flux, if it is more, the change in the flux will be more, the current will be more. If the current is more, the magnetic field which is opposing it will be more. I'll repeat. If flux is more, the change in flux will be more. By Faraday's and Lenz's law, EMF will be more, current will be more, the induced field will be more, the force which will oppose it will be more. That's it. So the induced field opposes the change in the flux as per Lenz's law. The induced field opposes the change, but it does not say why will it be more. See, understand the question. If turns increases, what is the bhavna? What is the sentence? The sentence is the turns increases, that's why the opposition increases. This just tells you, yes, there is opposition. But why does the opposition increase? That has not been told. Keep this in mind. Okay, people loved the way I drank water. No problem, guys. You can download that sound. I will definitely share this one day. Okay, I will probably make an audio file of me drinking water. Share it. Very satisfying. I read the comments. There is a link down here only. I'll show you where you can download. See, if you're watching this video, simple it is. Simple. Go down. Where is it? Instagram. You can see this link will open up my Instagram. Oh, that's me. You see this hero? Yeah, this is a hero. You can put some stars around him. Okay, so this is a superstar account. You should follow. He's particularly very popular down in South. Okay, So he's going to challenge Mahesh Babu and Rajnikant in the near future. So this is my Instagram account. Oh, that's me. All right. Anyways, let's not obsess over me. Then here you have my Telegram channel. This is actually our Enthuse Telegram channel. Just click on this and say join channel. That's it. Done. Perfect. All right. Chalo. Let's get going. And there we go. If the number of turns of a coil is increased, it becomes more difficult to push. Acha, this is done. Okay, moving ahead. Self-inductance may be called inertia of electricity. Due to self-inductance, opposing EMF is generated, and as a result of the change in the current or magnetic flux linked with the coil. What do you guys say? Thank you so much for all the smiles. Thank God I produced such nice smiles on the chat. Very good. Keep smiling, guys. Acha. D, A. It is B. How is it D? How is it A? It is a B. Thank you, Arpita. Tamil Terilma. Okay, so self-inductance may be called inertia of electricity. Yes, that is true. I'll tell you why. Just like energy stored in an inductor is half Li square, kinetic energy is half mv square. Can you see L and M similar to each other? I'll give you more proof like this. Flux is L into I, momentum is mass into velocity. This one. You can see current is similar to velocity. That's how it works. Inductor offers resistance to change in the current. Any resistance which is offered to change the current, that property is measured by inductance. That's what it is. Very good. And due to self-inductance, opposing induced EMF is generated. Perfect. As a result, there is a change in the current or flux. This is correct. This is what inductor does. But how is this a reason for this? How is this a reason? This is how it has been explained. See, understand the statement. It says it is called the inertia of electricity. Why is it called? That does not explain. Why is it called the inertia of electricity? That has not been explained. Understood, guys? So it does not explain why is it the electrical inertia. It just says it produces opposing flux, it produces opposing EMF, it produces current so that it creates opposition of the flux. But it does not explain why inertia. Why does it act like a resistor to changes in current? That has not been explained. That's the problem. I'm going to go with B. Mutual inductance becomes maximum when coils are wound over each other. Mutual inductance is independent of orientation of coils. Come on, let's go ahead. Thank you, Akash, for the lovely hearts. Keep it coming, guys. Keep it coming. Khushi saying A, Rishabh going with A, Uncharted saying C. Let's see, Ritesh going with A, Shreyas says C. Come on, my warriors. Veera saying D. Interestingo. The correct answer is actually C. Whoops. See, what happens when you have coil inside a coil and you have a coil inside of it, then the field which is produced by the outside coil, lot of field lines will flow through it. Imagine having this coil and having the red coil here. Imagine having the red coil here outside. Then what will happen? The field lines produced by this will just go like that. Hardly any field lines will go through the red coil. And if you, let's say for example, this is your primary coil and let's say it is producing magnetic field like this, but you place the other coil like that, then also the flux passing through it is different. So it definitely, it is not independent, it is dependent. Understand, it is not independent. Reason is wrong, reason is false. Assertion, it becomes more when the coils are wound over each other. So when you wind the coils over each other, maximum flux passes through it. Okay. So moment of inertia is not related with magnetic field, but they are all inertial properties, Kirtivasan. Inertia is resistance to change. Moment of inertia is also resistance to change rotation. Inductor is resistance to change electrical current. So they are all inertial properties but used for different applications. One is in translation, one is in rotation, one is in electricity. You take a copper sheet, place it in a magnetic field. If you pull it out of the field or push it, then we experience opposing force. So according to Lenz's law, eddy current is produced which opposes the motion of the sheet. Now what do you think? Thank you Anishka so much. Come on, let's do this. What do you think? I think it's based on a very important concept. I told you, you should read as a whole. Very important paragraph, a big paragraph with applications. I just marked it in this NCERT underline. A or C? Decide kar lo. It is actually A. Yep, this is completely based on eddy current. I just told you, very important chapter. So when you take a sheet and let's say there are field lines. Okay, there are field lines which are going, and if you move it, then what will happen? If you like to move it, then the flux will change. If the flux changes, then EMF will be created. If EMF is created, current is created. If current is created, I squared R loss is there. That's what has happened. So Lenz's law, eddy current opposes the motion of the sheet. Correct, because there are losses, and if you try to pull it or push it, you experience opposing force. Perfect explanation of this. Excellent. Moving ahead. When the number of turns in a coil is doubled, coefficient of self-inductance becomes 2 times. Coefficient of self-inductance is proportional to the square of number of turns. This question many students are going to make a mistake. No, balance game, it is related to Lenz's law because it produces opposing forces. It opposes. Lenz's law is related to opposing fields and opposing forces. So yes, when you move that coil or move that sheet, it does not create a force which will help it. It creates a force which will oppose it. That's why you experience some difficulty pulling it or pushing it. So that's why it is Lenz's law. Okay, so let's see how many of you can get this. Well, the correct answer is A is false, R is true. Oops, many students made a mistake. I just gave you one other formula. I marked it just some time back. Self-inductance is mu naught area N square L. Right? I just gave it to you. So, you can see coefficient is proportional to the square of number of turns. You can see that. So, if the number of turns are doubled, so if this is doubled, so 2 square will become 4 times. That means this L should also become 4 times. But here what does it say? It becomes 2 times. That is wrong. That is wrong. So that's why A is false. This is false. This is wrong. It is not becoming 2 times. This is correct. D. Yep. Got it? Very good, Vijayalakshmi. Now moving on to the next one. Motional EMF. What did I tell you? Motional EMF can come as case study. So here we have a case study on motional EMF. We have a rod of length L. It's on 2 rails. It's moving with speed V. There is a resistor. So based on that, you have a question. Take a screenshot. You see the symbol? Take a screenshot. Once the screenshot is done, put up a heart. Yep. Put up a heart once the screenshot is done, and then we will show you the questions. Very good. Everybody knows the formula. Now just use that formula over here. BLV, BLV, BLV. Very good. I can see all the hearts coming in, and here's the first question. Good and Bulgal back. Very good. There we go. What is the direction of the induced current in a wire which is moving in a field? So how do you think you are going to find it? Left hand rule, right hand rule, Ampere's rule, or right hand clasp rule? Yes, Tejeshwar, that's why I have put it in the case study. Case study, case study, case study. Case study mein you can have anything. Who did CBSE tell you that in case study they can give you only questions from whatever is there? No, right? The answer is left hand. No, right hand. What is this? Right hand. This is B, this is I, and this is basically your force. IL cross B. That's what it is. Fleming's left hand rule. So B is there, this is the current, okay, and this is your force. Left hand rule is not correct, it is the right hand rule. Okay, moving ahead to the next one. Very good, many of you know this. Okay, a conducting rod of length L moving in a transverse field with speed V. Resistance of the rod is R. The current in the rod is, what do you think is the current? Okay, no, L is in the numerator. BLV. L is in the numerator. Okay, students are clearly confused. Somebody saying A, somebody saying C, somebody saying B. My God, headache. I'm getting headache now. What is happening? Yeah, the resistance of the rod is R. See, this is that thing. You have that rod which is moving with V. So there will be EMF. How much is the EMF? It will be BLV. Because of this, there will be current which will be moving. But remember, there is resistance R. So how do I get the current? The current will be EMF by resistance. So it will be BLV by R. Is it there? Yes, option A. It's not difficult. Confirm A. Perfect. Confirmed A. Even I am confirming. It is A. Yes, Kirtivasan, what is your doubt about self-inductors? Probably you can leave it after the session is over in the comment section. I'll read all your comments. Yeah, I always do that. Okay, moving ahead to the next one. We have a 0.1 meter long conductor carrying some current, and it is held perpendicular to the field of this much value. The power required to move the conductor with a speed of, I think this was 1 meter per second. Okay, so just I'll correct it. This is 1 meter per second is how much? Come on, do this. All the options look similar. Probably you need to be very careful with the decimals. Ujjwal, if you have not studied EMI, then you have two options. If you feel like you are confident in other topics and you think you can spare some time, then watch my lecture. Other option is leave it, just read and see the questions and only see whatever I have underlined. Only whatever I have underlined in the NCERT, and only the questions which I am going to do today, tomorrow, day after, and through NCERT. That's all. Just do that much for EMI. Don't waste your time for EMI. Study other chapters properly. Okay, bacha log? Okay, C. Okay. Well. I think the answer is C. Yes, it is. And I'll tell you why it should be C. What is the question? The power. What is power? Power is force into velocity. What is force? Force is ILB. Remember, I just gave that to you. ILB in the previous chapter. So that means current. What is the current? Current is 50. What's the length? The length is 0.1. What is the field? 1.25 milli, which is 10 to the power minus 3. Into V. What is the V? 1 meter per second. Yes, in this slide it is correct. In the previous it was not. 15 to 0.1, that's 5 into 1.25 into 10 to the power minus 3. 5 into 1.25 is 6.25 into 10 to the power minus 3. So which is 6.25 milliwatts. Power is force into velocity. 11th standard formula has come to use over here. Very good. So Janya says she only found out the decimals. Yes, that will also work. Wow, we have reached the last chapter. Power is voltage into current. Well, how do you find the voltage, Hemant? That's another problem. Yes, Ridesh, whatever you have seen is enough. Whatever you are going to see in today's class is enough to score full marks. Okay, there we go. The last chapter. Let's open it up. I'm so excited. Finally, I will have my lunch. Okay, after this. But more than lunch, I'm more interested in you guys getting full marks. Chalo, open it up quickly, fatafat. Okay, current, what are the important things? Let's do this. It doesn't feel like, see, dekho, karte. So it's just a matter of starting. And I'm really proud of so many students who stayed till the start, from the start till the end. And initially it felt like, sir, how are we going to complete it? But yes, you are here on the last part of this lecture. So it's all possible. It's all a matter of starting it. And before you realize you would have done so much, and then you realize, yes, it's almost done. So the same way you need to push yourself even tonight, in the evening, tomorrow morning, day after, till your exams are over, and you will be able to do it. Okay? That's like my warriors. Let's go ahead. Introduction, fair enough. Yeah, please by heart this photo. Okay? This photo is very important. This can come in the exam. So this can come to draw. So if you do not draw him properly, if you forget the mustache, you get negative marks. That's what happens. And if you forget the coat, -2 marks, and if you forget the hair, -3 marks. So remember this, this is -1, this is -2 marks. If you forget the hair, -3 marks. So please remember this diagram properly, all right? Cool, great. Okay, let's go ahead. And oh yeah, I also forgot that if you add some shades over here, well, if you add some shades and if you make it look cool, then you can also get +10 marks. Yeah, you can get +10 marks if you add shades, because it looks cool, you know. All right, moving ahead. What do we have? What is this? Okay, so basic equation of voltage and current that is there over here, that's okay. Okay, that's fine, that's fine, that's fine. That's the derivation of RMS. So directly let's jump to RMS. Yep, there we go. This is definition of RMS. Now the concept, okay, in terms of RMS values, the equation and the relation between the current and the voltage are same. Okay, so I'll tell you what you need to do over here. Just go up. Okay, this is very important. To express a AC power in the same form of a DC power, a special value of current or voltage is used. That is called as root mean square or effective current, and it is denoted by IRMS or VRMS. Okay, looks like Kirtana is going to get full marks. Okay. Oh, by the way, that also reminds me, there is a new notification regarding OMR. Like earlier, I think you were marking it in small ABCD. Now it has to be in capital ABCD. So keep this in mind. It is not small ABCD, it is capital ABCD. Okay. Some new notice has come out. Okay. You can see the same formula is also there over here. IRMS is I by root 2. This is your max value. And remember this value, 1 by root 2 is 0.707 and root 2 is 1.414. Remember these important values. Go ahead. Now that's why you get power is IRMS square into R. That's very, very important. Okay, we go ahead, down. Okay, these are all standard things. Okay, these are all derivations. That's okay. Now here, yes, you need to remember reactance. The resistance is also called as inductive reactance, omega L, and current is voltage by resistance. Standard current is voltage by resistance. Here the resistance is called inductive reactance. Okay, very good. Then next, what do we have for capacitors? Okay, I'll come to that. Now this is okay, this is understood that inductors don't cause losses. That's understood. Only resistors cause losses. Capacitors or inductors do not cause any losses. Something which you need to know. They have derived it, but there is no need, because I'll tell you a simple fact. Inductors can store the energy, half Li square, and when needed it will give it back. So it does not cause loss, it stores it in half Li square. So because it stores, there is no loss. Okay, going ahead, they have unnecessarily complicated this chapter, I'll tell you, in a very, very weird way. Okay, this is actually such an easy chapter. XC is 1 by omega C, our current is voltage by resistance. XC is called as capacitive reactance. Reactance means equivalent of resistance, but for capacitors. So that's what it is. Go ahead. All this is fine. Okay, you need to know in the phasor diagrams. Okay, by chance if I missed it, let me put it over here. These phasor diagrams. Okay, but I'll tell you an easy way of remembering the phasor diagram towards the end. So that's why I did not, focus so much on the phasor diagram right over here. Okay, now this is LC oscillations. Yep, LC oscillations goes over here, and then LCR circuits. Okay, the phasor diagram, this looks very complicated, but I'll tell you an easy way. Now, yep, you need to know all these things. Let me tell you, it looks scary. It's very scary for most of the kids out here. What the hell is all this? So guys, although I'm marking it, please remember, I'll tell you easy ways tomorrow. Okay, tomorrow in the formula session. In the formula session, okay, you're going to see what are the easy ways to remember this. So you need to be there tomorrow at 11 o'clock so that you do not miss any of these things. So that's one thing that you need to know, and all of these formulas are important actually. But if you try and by heart it, you will be like, sir, this easy chapter, it's just numbers. What is this? Look at this crazy equations. Hold on, there are very easy ways. Don't go through this. Okay, it looks very, very complicated. But trust me, it is easy when you look at it the way I'm going to explain it to you tomorrow. And yes, resonance frequency, you need to know. This graph is important, definitely. And yep, sharpness, yep, you need to know about the sharpness, not this formula, my bad, oops, this formula. So the current is maximum for this particular value of frequency, which is the natural frequency. The maximum value is this much. So you define the sharpness when half of the power is being consumed, and then you have bandwidth. Yes, bandwidth formula, this one over here, and then where is that factor? Quality factor. Where did it go? Yes, there we have it. Quality factor. This is the quality factor. Okay, keep this in mind. Now, I'm just telling you, just remember these formulas, because even if you don't know the derivation, it's okay. It's okay, just fine. But I'll tell you, if you remember the formula and if the question comes on this directly, you will feel happy about it because you just applied the formula, you got the marks, that's all. That's what that matters right now, just 2 days before the exam. If we had 100 days, 200 days, then the things would be different. But we are just 2 days before the exam, keep this in mind. Okay, just go down. Now, yes, this is another important formula for power factors and all of that. You should remember this. Cos phi is also called as the power factor. Okay, keep this formula in mind. And the 3 cases, yes, you should know all these cases. When is it resistive? When is it capacitive? When is it inductive? Okay, just go through that. That's okay. LC oscillations, again, LC oscillations frequency is same as the resonant frequency. The charge and the current keeps oscillating up and down. The energy of oscillation is same as the energy of the charge stored in the capacitor, or the energy stored in the magnetic field of the inductor, one and the same thing. These formulas. Okay. Now go down. This table you need to know. See, the whole idea of LC oscillations is, if you have a spring mass system, okay, the time period is 2 pi under root m by k, and omega is root of k by m. But if you have inductor and if you have capacitor, then I'll tell you, inductor is similar to mass. I'll write it down over here. Okay, inductor is similar to mass. Capacitor is similar to reciprocal of spring. Okay, reciprocal of the spring constant. So because of that, what happens? It becomes very easy to write down the formulas. Like time period is 2 pi under root. Instead of mass, you will put inductance. Instead of spring constant, you will put reciprocal of C. So 1 by C. So it will become 2 pi under root LC. It becomes very easy to solve it. Same way, omega is root of k by m. K reciprocal is C. So 1 by C, and m is below. So that means L. So it will become just 1 by root over LC. So if you remember the analogues, force constant, spring, reciprocal of capacitance, mass, inductor. That's it. It becomes very easy to remember these formulas. That's all. Okay. Yep. I have not forgotten LCR. I just marked all the important formulas. And I told you I'll give you easier way to remember those formulas in tomorrow's class. So that's what I told you. I think I marked it somewhere here. Where did it go? Yep, I did it. Yeah. So I told you easy ways in tomorrow's class, in tomorrow's session, formula revision session, the LCR. I'm going to give it to you. Don't worry. All right? Yep. Cool. So going below, where are we? Yes. So this is done. This is done. This is done. 1 second. Okay. This is done. Yes. So I think we directly come to almost the end of the chapter over here. Oh yes, we have transformers. And in transformers, simple relationships that you need to know. Turns ratio formula. Okay. And you also need to know one more thing. Let's see. Current. Where is that current ratio? Yes, it's right over here. So this is that formula which you need to know. The currents ratio is inverse to the voltage ratio. Very, very important. And although some energy is lost, this is a good approximation since a well-designed transformer has an efficiency more than 95%. So very important. Transformers have hardly any losses. So because of that, you can use that input power is equal to output power. And then, yes, very important, these 4 points, the losses inside a transformer. The losses inside a transformer are because of the following reasons. This, and this. Flux leakage, resistance, eddy currents, and hysteresis. You should know these reasons. That's all. As simple as that. Yes, you can study from H.C. Verma also, bacha. And yep, summary also you cannot forget. And also the points to ponder. Where are our points to ponder? Yes, that's our points to ponder. Keep this in mind. Bas. So these are the important things from this chapter. Now in AC specifically, there are easy ways, there are better ways to look at all these formulas. And I prefer the H.C. Verma approach even for CBSE boards. So stay with me tomorrow at 11 o'clock. I'm going to show that to you. Okay, for now, let me just save this, but you'll get the PDF. Let's go to the questions coming up on your screen now. Ready for the last leg? Here it is. How to differentiate between RMS current and normal current in the question paper while handling numericals. Okay, very simple question. I'll tell you, Kirti Vasan, what you do. If nothing has been mentioned, it is RMS. But if it is something sine omega t, that something which is outside the sine is amplitude or the peak current. Or if they tell you this is the peak value, then you take it as the max or the peak current. If they don't tell anything, it is always RMS. Is that okay? Yes, Hemant, correct. You should use the vector format. Correct. That's what I'm going to show you. All right. Here we have it. RMS value is this much. Okay. Now here you can see this. Perfect example of that. See, 4 root 2 sine something. So this is your max value. The RMS, the peak value is this much. Yes, exactly. This is correct. Now what is RMS? RMS is peak divided by root 2. So 4 root 2 divided by root 2. Root 2 gone. 4 is the answer. Yep. 4 is the answer. Very good, very good, very good. But is the reason the correct explanation? Is the reason the correct explanation? Think about it. That's why it is not a lot of you thought this is correct, but what about this link? Where is that formula? RMS, okay, RMS is peak divided by root 2. This is the reason. Okay, this is the reason, but that is missing over here. It is missing. That is why the option B is correct. Do you guys get it? Yeah. So when does current lag? I'll tell you, simple way. Okay. See, if you want to remember the phasor diagram just for tonight, I'll give a simple trick. Current is always horizontal. Okay. Current in L, C, R circuit is horizontal. Perfect. This is L, C and R. Now, what is above everything? What's on the top of the world? What's above everything? Love is above all. Remember this statement. What is above all? Love is above all. That's it. That makes things very simple. So L, what is L? Inductance. So this VL will come here. Obviously VC will come below, opposite. And resistance will never have phase. So VR will come over here. Now the vector addition of all these three things gives you the total voltage. So So this is the vector addition of VL vector plus VR vector plus VC vector. Is this now simple? And then it becomes the phase difference. Phase between voltage and current. Phase. Got it. Simple. Very good. Done. Can we go ahead? Okay, I'm not sure why it is breaking. Selvarnaran, can you just come to Enthuse? That will be better. Okay. Thank you, Anandwana. All your love towards B. Thank you. Very good. So we'll deal with this in detail tomorrow in formula revision session. Stay with me for that. I'm going to teach you more tricks. Chalo, go ahead. Both AC and DC can be measured by hot wire instrument. Hot wire instrument is based on the principle of magnetic effect of current. Now you'll be like, sir, what is this hot wire instrument, sir? What is this hot wire instrument? Basically, any instrument which measures voltage or current based on the heat principle, heat loss principle. That is called as hot wire instrument. As simple as that. Okay. B. Uncharted saying no, sir. A is pakka. Kirtana saying A. Very interesting match between two people. Somebody is saying A, somebody is saying B. Very, very good. Very good. Let's see what it is. Okay. Miss Abhirami saying B. But it is C. Why is it C? Will exam be tough? Who knows? If it is tough, we'll deal with it. Anyways, we are going to do all the type of questions. So AC and DC can be measured with hot wire instrument. Yes. So if you have AC current or if you have DC current, how does it matter? At the end of the day, I squared R loss or I squared R loss, you can measure. So you can measure the heat, you can measure basically the temperature. From that, you can calculate current. So yes, you can use that. Hot wire instrument is based on the principle of magnetic effect. Wrong. It's based on the heating effect of current. What is it based on? Heating effect. Yeah. Cyberspace, I'll definitely ask the team to put it up in the description, but it might take some time. Just 1 second, my light just went off. Okay, 1 sec. All right. Yay, there we go. Done. Moving on. Next. Dimension of L by R is time. Oops. The time constant of L by R should be increased to reduce the rate of increase of current through a solenoid. Now, actually, this LR circuits, let's see how many of you can get this. Okay, I know Shimon sir will be waiting. I'll just end the class in another 10 minutes. Okay, more 10 minutes and I'm done. Okay, very good. Disha is saying, board par dekho, latak rahi hai chipkali. Arey, Disha, look behind you. There is a cockroach sitting behind you. It's flying cockroach, bada wala. Okay, so what is this? Yeah, so time constant, the time constant is basically L by R. That's fine. Now, that is okay. This time constant is basically in seconds, and that's therefore, you know, the dimension is time. But what about this? The time constant L by R should be increased to reduce the rate of increase of current through a solenoid. What happens when you increase time constant? If this is the current and if this is the time, then this is the time constant. If you increase the time constant, then what happens is that this graph shifts over here. So the rate at which the current increases will decrease. So check this out. Check this out. Both are correct. Both are correct. See, I'll explain again. If you increase the time constant is somewhere over here. If you increase it, this graph will go here. So the rate at which the current increases with time, it decreases. It's not so fast. It's correct. Dimension of L by R is also time. Perfect. But how is this the explanation? Please tell me, how is it explaining this? Why is it the dimension of time? It's not explaining that. So that's why it is B. That's why it is B. Understood? Very good. Moving on to the next one. At resonance, the current becomes minimum in a series LCR circuit. At resonance, the voltage and current are out of phase in series LCR circuit. Wow, interesting. Yes, Harshita, I know it was confusing, but I hope it made sense. You can, again, after the class, revisit those formulas. Okay. B or D? B or D? Well, the correct answer is D. A is false, R is also false. At resonance, current becomes minimum. Wrong. Wrong. Current becomes maximum. What are you guys saying? It does not become minimum, it becomes maximum. Remember the resonance curve? At resonance, the current becomes maximum for that particular frequency. At resonance, voltage and current are out of phase. Wrong. At resonance, the current is in phase with the voltage because the voltage across inductor and the voltage across the capacitor cancel out each other. So the total voltage is going to have zero phase difference with the current. Are not out of phase, they are in phase. Both are wrong. Both of them are wrong. D, correct. Correct, Suhani. They are in phase. How about this question? Come on, my warriors. When capacitive reactance is less than inductive reactance in a LCR circuit, then the EMF leads to, come on, figure this out. Just figure this out. Think about this. Come on, quickly. Just give me a second also. 1 second, come on. Keep posting your answers. Just 1 second. Okay, there we go. 1 second. Let me just adjust my chat. Okay, done. All right. Oh, where did we come? Okay, there we go. What are you guys saying? You're saying A. Some of you are saying B. Acha, kya baat hai? People are confused. I'll tell you what. When the capacitive reactance is less than the inductive reactance in a LCR circuit, EMF leads the current. Capacitive reactance, just like what I told you. Love is above all. So love is above all. Remember, this is love, this is capacitor, this is resistance. Okay. When capacitive reactance is less than inductive reactance, so capacitive reactance is less, so this is less, inductive is more, then the EMF leads the current. Yeah, so what happens is, if you add them vectorially, you will see the net addition will be somewhere here, because this vector is more than this. This is larger than this, so when you subtract the two, the difference will be here, resultant of this and this will be here. So you are going to see the net will be here, and you will see the voltage will be ahead of the current. Perfect. This is okay. The angle by which the voltage leads the current is given by this formula. Even if you use this formula, which I had just blocked, tan phi is XL minus XC divided by R, then you will see that L is more than C. So this is more. So this numerator is positive. That means phi is positive. That means voltage leads the current. Perfect. This is, yes, this is making sense. This is making sense. All of this is making sense. So hence the answer is A. It's perfectly making sense. No, it is not B. This is explaining it. This formula tells that XL is more than XC. So tan phi is positive. That's why it is leading it. That's why it is leading it. Understood? Okay, great. Amazing go. Thank you, Anishka. Let's get moving to the next one. A step-up transformer converts input low AC voltage to output AC high voltage. It violates the law of conservation of energy. It converts low to high voltage, so it's violating the law of conservation of energy. That's what it's saying. No, it is not XC minus XL, it is XL minus XC. Okay. Achha, the formula given in NCERT is ulta. I will teach you my formula, that way it will be easier. So wait for my tomorrow's session, it will be easier. Okay, it will be easier, don't worry. It doesn't matter. Even if it is ulta, it's just that you are taking some other direction as positive. That's all it means. Okay, that's what. Okay, so step-up transformer, yes. In a step-up transformer, the input voltage is increased So you increase the voltage, but you forgot that the input current, you decrease it on the output side. So the product of voltage and current remains constant. The energy is conserved, definitely. It violates. How can it violate? Wrong. It converts. Yes, that's correct. So A is true, R is false. Perfecto. Perfecto. Excellent. Understood? Let's get moving. And next question. A bulb connected in series with the solenoid connected to AC. If you place a soft core in the solenoid, the bulb will glow brighter. If you put some, soft iron inside the solenoid, the bulb will become brighter. That's what it says. When you introduce that core, then the inductance decreases. That's what it says. Okay, very interesting question. And let's see what happens. You have a bulb which is in series with the solenoid. So you have basically a bulb and you have it in series with a solenoid, basically L. And it is connected to a AC source. This is your AC source. Now, if you introduce some material here, what happens? Well, inductance is mu naught, remember area, into N square into L. But this mu naught is only true for vacuum. If you add some material, there will be some relative permeability. This will increase. Soft iron core will increase the permeability. So therefore, L will also increase. So inductance decreases. This is wrong. It will increase. So reason is wrong. Assertion is, I don't know. A bulb connected in series, if you introduce it, the bulb will glow brighter. Okay, so L will increase. If L will increase, omega L will increase. But what is omega L? Omega L is XL. If you remember, XL is omega L. Hence, XL will increase. XL will increase, that means what will happen? Think, V is IR. So voltage is I into resistance. So if X increases, resistance of that circuit will increases. So current will decrease. If current will decrease, the brightness will decrease. So basically the bulb will glow brighter. I think that is also false. Yes, D. It is not C, it is D. Okay. If voltage is increased, why can't current increase as per Ohm's law? That is wrong, Vignesh. That is only valid if the resistance is constant, and it is only valid for ohmic device. Transformer is not a ohmic device. And that's what I explained during Ohm's law. V is equal to IR is wrong for many devices. Understand that. Cool. Yes, all of them are wrong. A and R both are wrong. The bulb will not glow brighter. In fact, it will glow dimmer. Yep, that's the answer. Passage question for you. Okay. So Helvin, I'll just explain the last part again. See, what happens? Brightness. How does brightness depend on? It depends on current. How do you find current? Voltage is current into the resistance. Now what does resistance depend on? It is basically omega L. And what does L depend on? It depends on the material inside. So if you add some material, inductance increases, resistance increases, current decreases. Current goes down, what will happen? Brightness go down. That's why A is wrong. This says it becomes brighter. Wrong. Okay, take a screenshot. Take a screenshot quickly. Based on phasors, you can see voltage across the resistor, voltage across capacitor, voltage across inductor. Your simple LCR circuit, LCR series circuit. Okay, very good. Last few questions coming up on your screen right now. Last few questions, 3-4 questions, not more than that. Quickly, let's finish this. Done. A resistance is given, capacitance is given, inductance is given, joined in series, placed across this. What do you think is the total? What is the oh, they have not mentioned over here. I think the question is missing. I think this was supposedly, I think this was, what is the value of XL? So what is the value of XL? So that's the question. Just check this out, okay? So find the value of XL. Come on. Impedance, nahi. Impedance is one more question. I think there was XL. So figure this out. Inductance is given, right? So find out XL. What's the value of XL? Figure this out, my warriors. What are you getting this as? Okay, Kirti Vasan saying B. Come on, come on, come on, come on. D says Manoj. Oops, 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 oops. People making some mistakes. Some people are making mistakes, but many of you are getting it correct. I'm very happy with that. Excellent. So XL, what is the formula for XL? It is omega L. What is omega? Omega is 2 pi f into L. What is frequency? It is given 50 Hertz. So into 50. What is inductance? Inductance is 0.1. Okay. So it will become pi into 50, 2 5s are 10. So that 0 and 0.1 goes away. So it will be 3.14 into 10, which is 31.4 ohms. Is it there? Yes, it is there. 31.4 ohms. Very good. That's it. B. Very good. Many of you got it correct. Yes, it is. Next. Now the next question is, what is the impedance? Let's figure this out. Wow. What is the value of impedance? What is impedance? Just same as voltages. This is R. This is XC. This is XL. So the resultant of them. This is Z. If you are wondering how to find Z, just mark the height. The height is XL minus XC. This is Pythagoras. Use Pythagoras, you will get the answer. Come on, use Pythagoras. Z square will be R square plus height square, which is XL minus XC whole square. R resistance was how much? How much was the resistance? Ek baar check kar lo. I need to go back then. Okay. So just add the values of resistances and then finally take the root. See what is it coming out close to. Resistance was 12. Achha, so 12 square. Then XL was 31.4 minus, what was the value of XC given? XC was given to be something, square it. Just find this out approximately. Find this out approximately. Resistance was 12. Just check this out. What was the value of XC? This was 14. Okay, this was 14. So 31 minus 14, that's 17. 17 square, 289, right? So just do rough math. So this will be nothing but 17 square, roughly, approximately, which is roughly 289. This 12 square is 144. 144 and 289. 14, so 420, then this will become 433. Just check this out. 433. 433 is very close to 21's square. So I think it will be 21 point something. 21 point something. Sachin, bacha, you can also put it as XC minus XL. Then the manner in which you define phi will differ. That's all. It doesn't matter. Okay. So you can define it. But you will see XL minus XC will be better when you solve the questions. You will see why. Don't worry. Okay, yes, it is 21.13. Perfect. So that's how you can avoid a lot of calculations. You don't have to sit and figure out, how to find the root of a complicated decimal number. Just remember the square values. 21 square is 441. So it's very close to 433. So must be 21 point something. Cool. From the graph, which of the following is true? Graph means go back to this graph. This graph. Which of the following is true? Come on, figure this out. VL more than equal to VC, VL less than VC, VL more than VC, VL is equal to VC. What do you think? Yep. D, C. Yes, it is C. Guys, we just got XL as a 31.4. XC you guys just told me as 14 ohms. So XL is more than XC. So VL is also more than VC. That's it. You can see this right from the values. That's why option C is correct. In fact, in the graph also it was like that only. Very good. Now, final point before I end the session. There is a very important link which you might miss. Apart from all these things over here, there is a very important link. See, there is JEE crash course which is just going to start next week. Also, there is one crash course available for you which has just started this week. You have the option for joining any of them. You can see that right over here. Okay, the full schedule is there. One crash course also started on 6th of December. There is another crash course which started, then you'll have one more crash course. Where is it? Yeah, on 13th of December. Then there is one more crash course which has just started yesterday. You have all the options. Okay, and the timetable, everything is mentioned, and the entire syllabus of 11th and 12th will be revised with assignments, with test series till the 4th JEE mains attempt. If there are 4 attempts, if there are 10 attempts, there will be 10th attempt tak you will have validity. It will not end after the course ends. The course ends when JEE mains ends. You get all these things, and guess what the best part is? The light version and classic version both have a difference of 1000, but if you click on classic it becomes 9000. That's the magic. And how did that magic happen? Because of my coupon code SHHPRO. So what's the advantage of the classic version? Can you see this cross and this tick mark? This is for doubt solving on the mobile app. So if you want to get your doubts resolved, because I'm pretty sure after the boards you want your JEE preparation to go on, you don't want to miss it. So go ahead, join it, because the more you delay, your course will end later on. You might probably have some overlap with the first JEE mains attempt. You want this course to get over, you want the remaining time just for mock test and assignment. You don't want to sit and attend classes till the end of the exam, right? So make sure you join it. Even if you miss few classes, it's okay. You will get the recordings of all the live classes. So that's something which you need to go ahead and click, buy the course. It's just 9,000 bucks. Okay, so how is the combination of inductors different from resistors? Inductors add the same way as resistors, in series or in parallel. Okay, so we had a 5-hour 20-minute session. I think now it's time for me to have my lunch finally. And thank you very much. Do leave comments after the session ends. I will read all your comments. Thank you so much for being here. Study well. See you tomorrow at 11 o'clock. What are we going to do? Formula revision with application. That's it for tonight, and take care. God bless you all. Study well, take care, stay healthy, stay safe. Hasta la vista. This was Shreyas here.